Part 1. The Invisible Architecture. Right now, you are sitting inside a structure so vast, so intricately layered, and so deliberately hidden from your senses that even the best telescopes humanity has ever constructed cannot fully reveal it. Not because the technology is failing, not because we haven't looked hard enough, but because the universe, by its very nature, keeps the most important things wrapped in a darkness that light itself cannot penetrate. We tend to think of space as something we can eventually see if we just build a big enough instrument, point a telescope at the sky, zoom in again, and eventually reality will reveal itself. That is how humans have been thinking about the cosmos since Galileo first turned his lens toward the moon. The idea that observation equals knowledge, that the universe is fundamentally visible, that if something exists, it will eventually show itself in some wavelength of electromagnetic radiation, some flicker of energy, some detectable trace. That idea is wrong. The universe is not mostly visible. It is mostly hidden, and not hidden in some poetic or philosophical sense. Hidden in the most literal, measurable, physically precise sense that physics allows. The matter you can see, every galaxy, every nebula, every glowing gas cloud, every star that has ever been cataloged in every survey ever conducted, all of it together amounts to less than 5% of the total energy content of the universe. The remaining 95% is composed of things that do not emit light, do not absorb light, do not interact with the electromagnetic force that governs everything our instruments are designed to detect. We have named them. We have modeled their effects. We have measured the gravitational fingerprints they leave on the things we can see, but we have never directly detected a single particle of either of them. That is the situation we actually live in, a universe where the visible world is an extreme minority, a tiny luminous fraction floating inside a much larger, much stranger, and almost entirely unobservable cosmos. And it gets stranger than that, because even within the observable portion of the universe, the part made of ordinary matter that our instruments can theoretically detect, there are things hidden behind physical barriers that no technology will ever breach. Not because science hasn't progressed far enough, because the barriers are written into the geometry of space-time itself. Light from those regions will never reach us. Not in a billion years. Not in a trillion. Not ever. The universe has drawn permanent curtains around portions of itself, and it drew them using the same laws of physics that govern everything else. The hiding is not an accident. It is a structural feature. Then there are the things hidden not by distance or by darkness, but by scale. Things happening at energy levels so extreme, in conditions so far beyond anything achievable in a laboratory, that we can only ever infer them indirectly. The first moments of the universe, before even light had room to travel. The interior of a black hole, where all the physics we understand breaks down and something else takes over that we have not yet managed to describe. The precise moment of antimatter's disappearance, when the universe chose confer over its mirror image in some process that should not have happened and yet clearly did. This is a story about those hidden things, not a list of curiosities. A genuine tour of the parts of the universe that are actively concealed from human perception and what we have managed to learn about them anyway through indirect evidence, gravitational inference, mathematical extrapolation, and the kind of careful, patient scientific reasoning that sometimes knows something long before it can see it. We are going to travel through the invisible architecture of the cosmos, layer by layer, from the grandest structures that bend the paths of entire galaxy superclusters, down to the quantum-level mysteries that may determine why anything exists at all. By the end of this, the question will no longer be why the universe hides so much. The question will be whether it's hiding something even deeper, something that our current physics doesn't yet have a name for. Let's start with scale, because before you can appreciate what's hidden, you need to feel the size of what contains it. The observable universe is a sphere roughly 93 billion light-years across. That number is almost meaningless to a human brain that evolved to navigate distances of a few hundred miles. So consider it this way. If you shrank the entire observable universe to the size of the planet Earth, the Milky Way galaxy, with its 400 billion stars and its 100,000 light-year diameter, would be a single grain of sand on that planet's surface. And within that grain of sand, The solar system would be a structure so small it could not be resolved with an optical microscope. That is the scale of what we are talking about. At that scale, the visible galaxies form a network, sometimes called the cosmic web. They are not distributed randomly. They cluster along enormous filaments, thread-like structures hundreds of millions of light-years long, and those filaments form the boundaries of vast empty regions called voids, which we will explore in detail later. The whole thing looks, when rendered in computer simulations, uncannily like a three-dimensional neural network, nodes where filaments intersect, dense clusters of thousands of galaxies packed into a region the width of a large void's radius. Sheets of galaxies stretched flat along the boundaries between neighboring empty spaces, and enormous nothingness filling most of the volume. This structure, the cosmic web, is the largest visible architecture in the universe, and we know, from multiple lines of converging evidence, that this visible architecture is a minority feature of a much larger and far more massive invisible architecture. The filaments glow because they contain ordinary matter that forms stars. But the gravitational scaffolding that holds those filaments in place and determines their shape is made of something else entirely. Something that doesn't glow. Something that has never been directly detected despite nearly a century of searching. We also know, from the way that everything in our local cosmic neighborhood is moving, that there is a gravitational pull coming from behind the plane of the Milky Way. A pull so strong that it is deflecting the paths of hundreds of thousands of galaxies, including our own, toward a single point in the sky that we mostly cannot see. Something massive is hiding there, behind the thickest part of our own galaxy's disk. Something we are falling toward, slowly, inexorably, across hundreds of millions of years. And we know that the expansion of space itself is accelerating. That the universe is not just expanding, as Edwin Hubble first demonstrated in 1929, but expanding faster and faster, driven by a form of energy so uniform, so perfectly distributed, and so completely unlike any kind of matter or radiation we have ever encountered, that it sits in our equations as a placeholder, a cosmological constant, a symbol we use to mark the place where a real explanation should eventually go. These are not peripheral mysteries. They are central ones. The hidden things are not footnotes to the story of the universe. They are the main characters. They outnumber, outmass, and outpace everything we can see. The visible universe is the afterthought. So let's go find it. Let's go see what's hiding. Drop a comment right now telling us where in the world you're watching from and what time it is there. We love seeing how far this reaches. And if this is your first time here, hit subscribe. We are just getting started. Part 2. The Great Attractor and the River of Galaxies. Imagine standing on a riverbank and watching the water flow past. Now imagine that every fish in the river, every log, every leaf, every molecule of water is also moving downstream and has been moving downstream for billions of years, and you are also in the river. And the riverbank you think you're standing on is actually the inside of a current, and the entire river is tilted slightly toward a waterfall that is so far away you cannot see it, even though every single thing in the river is definitely heading toward it. That is roughly analogous to our actual situation in the local universe. Everything in our cosmic neighborhood is moving. Not just the expansion of space, which carries galaxies apart from each other as the fabric of the universe stretches, but a separate, additional motion, a peculiar velocity in the technical language of cosmology, a bulk flow, a common direction of travel that affects the Milky Way, the local group, the Virgo cluster, and hundreds of thousands of other galaxies across a region, spanning more than 500 million light-years. Everything is moving toward something, and for most of the 20th century, we could not see what it was. The region responsible was first identified as anomalous in the 1970s and 1980s, when cosmologists studying the peculiar motions of galaxies found that the standard model of cosmic expansion, in which galaxies move apart from each other purely due to the stretching of space, was not the whole story. There was an additional component. A bulk flow in the direction of the constellation Centaurus. Hundreds of galaxies, then thousands, then hundreds of thousands, all sharing a common drift in the same direction. Something was pulling them, something was pulling us. The problem was simple and infuriating. The source of this pull lay almost exactly behind the plane of the Milky Way. The dense disk of our own galaxy, packed with stars, gas, dust, and the obscuring murk of the interstellar medium, sits directly in the line of sight to the object responsible. Invisible light, looking in that direction, is like trying to see a city on the other side of a wall made of cotton. The galactic plane absorbs, scatters, and re-emits nearly all of the optical light trying to pass through it. Astronomers call this region the zone of avoidance, which is one of those names in science that manages to be both descriptive and somehow ominous at the same time. The pull is real, the source is hidden. That combination was deeply unsatisfying to cosmologists, who spent decades trying to peer through the obscuring disk using wavelengths of light that could slip past the dust and gas. Radio waves, infrared, X-rays. Slowly, a picture began to emerge. What lies behind the veil is not a single massive object. It is a gravitational basin. A region of space containing an extraordinary concentration of galaxies, galaxy clusters, and presumably vast quantities of dark matter. The most prominent galaxy cluster visible in this region is the Norma cluster, also called a Bell 3627, a densely packed group of hundreds of galaxies sitting about 220 million light-years from Earth. But the Norma cluster is just the brightest landmark in a much larger structure. It sits near the focal point of something enormous. In 2014, a team of astronomers led by Brent Tully published a paper in the journal Nature that reorganized our understanding of cosmic geography. They used maps of galaxy velocities, the peculiar motions of thousands of galaxies relative to the Hubble expansion, to define what they called basins of gravitational attraction. The logic was elegant. If gravity is pulling all the water toward a drain, you can map the basin by tracing where all the water is flowing from. Do the same thing with galaxies, and you can define regions of gravitational coherence. What they found was that the Milky Way, the Local Group, the Virgo supercluster, and roughly 100,000 other large galaxies, spanning about 500 million light-years, all sit inside a single gravitational basin. They named this basin Laniakea, a Hawaiian word meaning immense heaven or open skies. Laniakea is a supercluster, but not a supercluster in the old sense of a region where galaxies happen to be clustered. It is a dynamic structure, a volume of space whose member galaxies are all being funneled gravitationally toward a common focal point. And that focal point is the Great Attractor, sitting in the dense region behind the galactic plane. The Great Attractor has a mass on the order of 10 to the power of 16 solar masses. Written out, that is, a 1 followed by 16 zeros. In comparison, the Milky Way has roughly 1 trillion solar masses, which is a 1 followed by 12 zeros. The Great Attractor outweighs our galaxy by roughly 10,000 to 1, is less than BR, is greater than. And yet we are not being pulled toward it at tremendous speed, because distance is enormous, and the gravitational effect, while real, is measured in hundreds of kilometers per second rather than thousands. Our local group is drifting toward the Norma cluster region at roughly 600 kilometers per second relative to the cosmic microwave background. That sounds fast until you realize that the distance involved is hundreds of millions of light-years, and at that velocity, it would take something in the range of 1 trillion years to actually reach it, by which time the universe will have expanded far past the point where such a journey has any meaning. But here is where the story deepens even further. A 2024 study published in Nature Astronomy by Valade and collaborators, mapping the gravitational basins of attraction in the local universe with unprecedented precision, found strong evidence that Laniakea itself is not the end of the story. The entire Laniakea supercluster appears to sit within a larger gravitational basin, one that is pulling it and us toward the Shapley concentration. The Shapley concentration is the most massive structure in the nearby universe that we know of. It sits about 650 million light-years away, also partially hidden behind the galactic plane. It contains dozens of rich galaxy clusters, thousands of individual galaxies, and a mass estimated at more than 10 million billion solar masses. Even at that distance, its gravitational influence is detectable. The flows of galaxies in our part of the universe show a clear component in the direction of Shapley, layered on top of the flow toward the Great Attractor. And in 2025, a team using the Meerkat radio telescope in South Africa, as part of a survey called CF4++, published evidence for yet another massive hidden structure, the Vela supercluster. Partially obscured by the zone of avoidance and only accessible through radio observations that can penetrate the galactic dust, the Vela supercluster sits roughly 800 million light-years away and has a mass that preliminary analyses suggest rivals the Shapley concentration. Its full extent and its contribution to the bulk flows of our local universe are still being mapped. We live, in other words, in a cosmic region that is being pulled toward one hidden structure while also being influenced by others even further away. There is no simple answer to the question of what everything in our neighborhood is ultimately moving toward, because the gravitational influences are multiple and layered, and the full picture requires surveys that peer through the very part of the sky we can see least well. What we can say is this: the universe has large-scale structures, far more massive than the galaxies that glow within them. Those structures are defined not by visible matter, but by gravitational flow patterns. And the most significant of them, the ones that are actively reshaping the trajectories of hundreds of thousands of galaxies, are hidden from optical telescopes behind the plane of our own galaxy. We are inside the current, and the waterfall is behind a wall, and we can hear its pull in the motions of everything around us. The zone of avoidance is a genuinely poetic name for something genuinely strange. It is the direction in the sky that astronomers have historically been able to see least well, and it turns out to be the direction from which some of the most consequential gravitational forces in our local universe are emanating. The universe arranged its most interesting local structure in the one spot where we have the hardest time looking. Whether that is a coincidence or simply a consequence of our location inside a galaxy that formed along a filament that points roughly toward the Great Attractor, is something cosmologists continue to debate, but the effect is the same. Some of the most important things shaping our cosmic neighborhood are hiding in plain sight, behind a wall of starlight we cannot see through. Part 3. Dark Matter, the Ghost Scaffolding. Here is a fact that should genuinely unsettle you. The matter you are made of, the matter that makes up every atom in your body, every atom in the chair you're sitting in, every atom in the earth, the sun, the moon, every star you can see in the night sky, every galaxy that has ever been photographed, every nebula, every planet, in every solar system, in every corner of the observable universe, all of that ordinary, familiar, visible matter adds up to less than 5% of everything that exists. The remaining 95% is composed of things we have never directly detected, never caught in a detector, never identified as a specific particle or field. About 27% of that total is what we call dark matter. The name is misleading because it suggests we know what it is and have simply established that it does not emit light. In reality, the name is a placeholder. Dark matter is a label for the gravitational anomaly. It is the name we have given to the discrepancy between the amount of mass we can see and the amount of mass required to explain what we observe. It is a name for the mystery, not the solution. The first person to take the anomaly seriously was Fritz Zwicky, a Swiss-American astronomer working at Caltech in the 1930s. Zwicky was studying the Coma cluster, a dense collection of hundreds of galaxies, about 320 million light-years away. By measuring how fast the individual galaxies in the cluster were moving relative to each other, he could calculate how much mass the cluster would need to have in order to hold itself together gravitationally at those velocities. The answer was dramatically larger than the mass he could calculate from the visible galaxies, by roughly a factor of 400. Zwicky concluded that there must be an enormous amount of mass in the cluster that was not visible. He called it dunkle materie, dark matter. The scientific community largely ignored this for several decades. It seemed like a calculation error, a measurement artifact, something that would resolve itself when better data became available. Then Vera Rubin arrived. Working in the 1960s and 1970s, Rubin was measuring the rotation curves of spiral galaxies. When you look at a galaxy like the Milky Way from above, you see stars orbiting the galactic center. Basic Newtonian mechanics predicts how fast those stars should be moving at different distances from the center, the same way we can predict how fast the planets orbit the Sunday. Stars closer to the dense central bulge should orbit faster. Stars in the outer regions, where the visible mass is sparse, should orbit more slowly, just as the outer planets of the solar system move slower than the inner ones. Rubin found the opposite. Star velocities in the outer regions of spiral galaxies were not declining, they were flat. Stars at the very outer edges of galaxies were moving just as fast as stars near the center, and in some cases, slightly faster. This was not a small discrepancy. It was a categorical violation of what the visible mass predicted. The outer stars were moving so fast that, by gravitational calculation, they should have been flying away into intergalactic space billions of years ago. The galaxies should have come apart. They did not. The only explanation consistent with the physics was that there was far more mass in these galaxies than was visible, not just a little more, dramatically more. And this invisible mass had to be distributed in a large, roughly spherical halo extending well beyond the luminous disk, because that distribution was needed to explain the flat rotation curves. A concentrated central mass would produce the declining outer velocities that Newton predicts. Only an extended spherical halo could produce the flatness that Rubin measured. Rubin's observations, confirmed by dozens of subsequent researchers across hundreds of galaxies, established beyond reasonable scientific doubt that there is something out there, something massive, invisible, distributed in halos around galaxies and filling the spaces between them in galaxy clusters, something that interacts gravitationally with ordinary matter, but does not emit, absorb, or scatter electromagnetic radiation in any detectable way. Additional evidence piled up over the following decades. Gravitational lensing. When light from distant objects passes near a massive galaxy cluster, the gravity of the cluster bends the light, distorting the images of objects behind it. By measuring how much bending occurs, you can calculate how much mass is doing the bending. That calculated mass is consistently far larger than the visible mass of the cluster. And the distribution of the lensing mass matches exactly what you would expect from a dark matter halo, not from the distribution of luminous galaxies. The bullet cluster, observed in detail in the early 2000s, provided perhaps the most direct visualization of dark matter's existence and separability from ordinary matter. The bullet cluster is actually two galaxy clusters that collided about 150 million years ago. When galaxy clusters collide, the galaxies themselves mostly pass through each other because galaxies are small compared to the distances between them, and they interact gravitationally, but rarely collide directly. The hot gas in the clusters, which constitutes most of the ordinary matter, does collide and interact electromagnetically, slowing and heating dramatically, and producing a characteristic bright X-ray emission in the region of the collision. When astronomers mapped both the X-ray emission, showing where the ordinary matter was, and the gravitational lensing signal, showing where the mass was, they found that the two maps did not overlap. The gas was concentrated in the center, where the collision had slowed it, but the gravitational mass was distributed in two distinct clumps on either side, corresponding to where the dark matter halos of the two clusters had passed through each other, with essentially no interaction. Dark matter, whatever it is, does not interact with itself or with ordinary matter through the electromagnetic force. It passed right through the collision. The bullet cluster is the closest thing to a direct visual proof of dark matter that we have. Not of what dark matter is, but of what it does and how it behaves differently from ordinary matter. As of 2025, the search for a specific particle that could be dark matter has been running for several decades without a confirmed detection. The Lux Zeppelin detector, a 10-ton tank of ultra-pure liquid xenon sitting a kilometer underground at the Sanford Underground Research Facility in South Dakota, completed its largest ever data set in late 2025, covering 417 live days of operation. It found no evidence of weakly interacting massive particles, WIMPs, between masses of 3 and 9 giga-electron volts. The LZ experiment's results set world-leading constraints above 5 giga-electron volts, eliminating a substantial portion of the WIMP parameter space that had previously been considered viable. This is significant. WIMPs were for decades the leading candidate for dark matter. They are hypothetical particles predicted by supersymmetric extensions of the standard model of particle physics. They interact through the weak nuclear force and gravity, but not through electromagnetism. They would have been produced in the right abundance in the early universe to account for the observed dark matter density. They were, in theory, exactly what dark matter should be. And experiment after experiment, detector after detector, has failed to find them. The field has shifted. Alternative candidates are now receiving more serious attention. Axions, extremely light particles, first proposed as a solution to a different problem in particle physics, are being searched for by specialized detectors that look for their conversion into photons inside strong magnetic fields. Primordial black holes, tiny black holes formed in the extreme density fluctuations of the early universe, have not been ruled out as a contributor. Sterile neutrinos, hypothetical relatives of the known neutrinos that interact only through gravity, remain candidates. In November 2025, a researcher at the University of Tokyo published a reanalysis of 15 years of data from NASA's Fermi Gamma Ray Space Telescope, identifying a halo of gamma-ray emissions spreading from the galactic center that closely matches the theoretical signature of dark matter particle annihilation, though the scientific community received the claim with significant skepticism, noting that the signal could have other explanations. The situation in dark matter physics is one of the most productive and frustrating in all of science. The evidence for dark matter's gravitational effects is overwhelming, consistent, and confirmed by multiple independent methods. The identity of the particle, or particles, or whatever it actually is, remains completely unknown. The universe has arranged its most abundant form of matter in a configuration that is gravitationally influential, but electromagnetically invisible, and it has done so in a way that resists every detection method we have attempted. There is also a minority hypothesis worth taking seriously. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in 1983, suggests that Newton's law of gravity breaks down at the very low accelerations characteristic of the outer regions of galaxies. Under MOND, no dark matter is needed to explain flat rotation curves. A modified gravitational formula does the work instead. MOND works remarkably well at the scale of individual galaxies. It works poorly for galaxy clusters and cannot explain the bullet cluster observations without significant additional assumptions. Its greatest difficulty is that it has not yet been successfully incorporated into a complete relativistic theory that passes all the tests of general relativity. The scientific mainstream treats MOND skeptically, but it has not been definitively ruled out, and it continues to attract serious research attention because it makes highly accurate predictions for galaxy rotation that dark matter models struggle to reproduce in their details. The full picture may ultimately involve elements of both. For now, dark matter is the universe's most successful known unknown. We know it's there. We know it outweighs ordinary matter by roughly 5 to 1. We know it forms halos around galaxies and clusters and provides the gravitational scaffolding around which the cosmic web is organized. We know it does not emit, absorb, or scatter electromagnetic radiation at any wavelength, and we do not know what it is. The universe keeps its most abundant form of matter behind a wall of perfect electromagnetic invisibility, and that wall has not yet been breached. Part 4. Dark Energy, the Accelerating Tier. In 1998, 2 independent teams of astronomers announced a discovery so unexpected that it upended decades of cosmological thinking and eventually won its leaders a Nobel Prize. They had been studying type Ia supernovae, a class of stellar explosion that occurs when a white dwarf star accretes matter until it reaches a critical mass and detonates in a catastrophic thermonuclear explosion. Type Ia supernovae have a remarkable property. They all explode with roughly the same peak luminosity. This makes them standard candles. By comparing how bright they appear in the sky against how bright they actually are, you can calculate how far away they are with high precision. What both teams found, independently, using supernovae in galaxies billions of light-years away, was that those distant supernovae were dimmer than expected, not slightly dimmer, consistently, measurably dimmer across their entire sample, and dimmer meant farther. The distant galaxies containing those supernovae were farther away than they should have been if the universe had been expanding at a steady rate, or even decelerating due to gravity, as most cosmologists expected. The only explanation was that the expansion of the universe was accelerating, Space was not just expanding, it was expanding faster and faster over time. This was not supposed to be possible, or at least not without some new physics. The standard expectation had been that the gravity of all the matter in the universe would gradually slow the expansion down over cosmic time. The question was whether there was enough matter to eventually stop the expansion and reverse it into a big crunch, or whether the density was too low and the universe would expand forever, but at a decelerating rate. What nobody expected was acceleration. Something had to be providing a repulsive force, something with negative pressure, in the language of thermodynamics. Something fundamentally unlike any form of matter or radiation that physics had previously described. That something is called dark energy. Dark energy is, in a certain sense, the name for our ignorance written into an equation. In Einstein's general relativity, there is a term called the cosmological constant, represented by the Greek letter lambda, which Einstein himself added to his equations in 1917 and later withdrew when Hubble's discovery of cosmic expansion made it unnecessary. The cosmological constant acts as a uniform energy density of space itself. Positive cosmological constant means space has a positive energy density that creates an effective repulsive pressure. Einstein called it his greatest blunder when he thought it was wrong. It turns out to be the best mathematical description we currently have for whatever is driving the acceleration. The numbers involved are simultaneously enormous and bafflingly small. Dark energy accounts for roughly 68% of the total energy content of the universe. It is by far the dominant component. And yet the value of the cosmological constant, when we measure it from the supernovae data and from the precise mapping of the cosmic microwave background, is fantastically tiny. It corresponds to an energy density of about 6 × 10⁻⁻10 joules per cubic meter. That is a phenomenally small amount of energy, spread uniformly across the vast emptiness of space. The problem is that when physicists try to calculate what this value should be from quantum field theory, the answer they get is approximately 10 to the power of 120 times larger than the observed value. That discrepancy is the largest mismatch between theory and observation in the history of science. It is not a small error. It is 120 orders of magnitude. Physicists call it the cosmological constant problem, and it is one of the deepest unsolved puzzles in fundamental physics. Theoretical proposals for what dark energy actually is include quintessence, a dynamic scalar field that fills space and whose energy density changes slowly over cosmic time, unlike the true cosmological constant, which would be fixed. If dark energy is quintessence rather than a cosmological constant, the acceleration of the universe could have been different in the past, could change in the future, and could potentially even reverse. Some models of quintessence predict that the universe will eventually stop accelerating and even contract. The most significant recent development on dark energy comes from the Dark Energy Spectroscopic Instrument, known as DESI. DESI is a ground-based telescope at the Kitt Peak National Observatory in Arizona, equipped with 5,000 robotic fiber positioning devices that can simultaneously measure the spectra of 5,000 galaxies at once. By observing baryon acoustic oscillations, the imprint left in the distribution of galaxies by sound waves in the early universe that can serve as a standard ruler, DESI can measure how the expansion rate of the universe has changed over cosmic time. Results from DESI, published in 2024 and refined in 2025, provided evidence that dark energy may not be a fixed cosmological constant. The DESI data show hints that the effective dark energy equation of state parameter, which measures how dark energy's density changes as space expands, has evolved over the last several billion years. The observations suggest a possible deviation from the behavior expected of a simple cosmological constant, with the data preferring a scenario where dark energy was somewhat stronger in the past than it is today, or where its properties have changed over time. These results are preliminary and contested. The statistical significance of the deviation from a simple cosmological constant was not overwhelming in either the 2024 or 2025 DESI analyses, and systematic errors in the measurements cannot be entirely ruled out. But the results motivated significant theoretical activity, and the possibility that dark energy is dynamic rather than constant has become a mainstream scientific hypothesis rather than a fringe speculation. Layered onto the dark energy puzzle is the Hubble tension, which may be the most consequential, unresolved problem in modern cosmology. The Hubble constant, h0, measures how fast the universe is currently expanding per unit of distance. Two independent methods of measuring it give different answers. Measurements based on the early universe, specifically the cosmic microwave background as mapped by the Planck satellite, give a value of about 67.4 kilometers per second per megaparsec. Measurements based on the local universe, using type Ia supernovae calibrated by Cepheid variable stars, consistently give a value around 73 kilometers per second per megaparsec. That 9% discrepancy, measured with extraordinary precision by both methods, has now exceeded 5 sigma in statistical significance. In physics, 5 sigma is the threshold for declaring a discovery or, in this case, a problem. The two measurements are not compatible with each other within the standard cosmological model. Either one or both measurements have unidentified systematic errors, or the standard model is incomplete, and something about the early or late universe is different from what we think. Dark energy that is not perfectly constant could contribute to resolving the tension. New physics in the early universe, such as a brief burst of early dark energy before the cosmic microwave background was emitted, could also help. But no single proposed solution cleanly resolves the tension without creating new problems elsewhere. And, as of the time this was written, the Hubble tension remains open. The situation with dark energy is even more philosophically challenging than with dark matter, because we cannot even clearly define what we are looking for. Dark matter is presumed to be a particle or a collection of particles with definite properties that we could in principle detect if we built a sufficiently sensitive instrument. Dark energy might be a fundamental property of space-time itself, not a thing at all in the particle sense, but the geometry of the vacuum. Searching for it is less like hunting for a particle and more like asking why space has the shape it has. That is not a question that particle detectors answer. The universe is accelerating away from itself, driven by something we cannot see, cannot detect, and cannot explain from first principles. The expansion will not stop. Galaxies beyond a certain distance, called the Hubble radius, are already receding from us faster than light, not because they are moving through space at superluminal speeds, which special relativity forbids, but because the space between us and them is expanding faster than light can cross it. Over time, as the expansion continues to accelerate, more and more of the currently observable universe will cross the cosmological event horizon and become permanently inaccessible. The last photons from those galaxies will have already left their sources. The light is en route. But everything that happens in those galaxies after their light has cleared, the horizon will never be seen by any observer in our region of the universe. Dark energy is not just hiding matter. It is actively shrinking the portion of the universe that is, in principle, observable. It is writing the ending of the universe's accessibility to itself, one galaxy at a time, across billions of years. Part 5. Secrets in the oldest light. There is a wall in the universe. Not a physical wall, not made of anything you could touch or photograph directly. A wall made of time. A wall made of the moment when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, about 380,000 years after the Big Bang. Before that moment, the universe was a hot, dense plasma, and light could not travel freely through it. Photons were constantly scattered by free electrons, bouncing around like sound waves in a crowded room. After that moment, the universe became transparent, and those photons were free to travel. The light released at that moment of transparency has been traveling through the universe ever since. It has been stretched by the expansion of space from the high-energy radiation of a hot plasma into microwaves, with a temperature today of about 2.725 degrees above absolute zero. We call it the cosmic microwave background, the CMB, and it fills the entire sky in every direction. Every microwave photon you detect from the CMB has been traveling since roughly 380,000 years after the Big Bang. It is the oldest light in the universe, and it is one of the most precisely mapped objects in science. The Planck satellite, launched by the European Space Agency, spent years producing detailed maps of the temperature of the CMB across the full sky, with angular resolution down to about 5 arc minutes and temperature precision of about 1 part in a million. The result is a portrait of the universe as it existed when it was less than a millionth of its current age. And in that portrait, there are things that should not be there. The CMB is nearly uniform. The temperature varies by only about 1 part in 100,000 across the sky, confirming that the early universe was extraordinarily smooth and homogeneous. Those tiny temperature variations represent slight density differences in the early universe plasma, regions that were marginally denser or less dense than average. The denser regions would eventually collapse under gravity to form the first galaxies. The pattern of these fluctuations is predicted by inflationary cosmology and the standard model of cosmology with remarkable precision. The CMB is, in most respects, a spectacular confirmation of our understanding of the universe's birth. But not in all respects. There is a cold spot. In the direction of the constellation Eridanus, the CMB has a region that is significantly cooler than surrounding areas. Not the tiny fluctuations of 1 part in 100,000 that you expect from quantum fluctuations in the inflationary epoch. A large, cold patch with a temperature depression of about 70 microkelvin below the mean. It was first identified in 2004 inches data from NASA's WMAP satellite. The European Space Agency's Planck mission confirmed it in 2013, ruling out the possibility that it was an artifact of the WMAP instrument. Both independent satellites see the same cold spot in the same location. The cold spot is too large, too cold, and too circular to be explained by the standard model's predictions of CMB temperature variations. At its scale, the probability of producing such a feature purely from random quantum fluctuations in the inflationary epoch is estimated at less than 2% under standard cosmology. That is not nothing, but it is the kind of anomaly that cosmologists take seriously, especially when it persists across multiple independent measurements. The most prosaic explanation is that a supervoid, an enormous region of space with far fewer galaxies than average, sits between us and the CMB in the direction of the cold spot. When light from the CMB passes through a large, underdense region, the integrated Sachs-Wolf effect predicts that it will lose a small amount of energy, producing a cold spot in the microwave sky. A team using data from the Dark Energy Survey found a correlation between the location of the CMB cold spot and an approximately 1 billion light-year diameter void in the cosmic web they called the Eridanus supervoid. But the supervoid they identified is probably not large or empty enough to fully explain the cold spot's temperature depth. The full explanation remains unclear. More exotic proposals include a cosmic texture, a topological defect left over from a phase transition in the early universe, similar in concept to the cracks that form when water freezes, but written into the fabric of space-time, or a bruise from a collision with another bubble universe in a multiverse scenario, a bubble collision that would have left a distinctive imprint in the CMB pattern. These ideas are genuinely speculative, and evidence for them is not compelling, but they have not been ruled out. Then there is the axis of evil, a name coined by cosmologists with a sense of drama for an alignment in the CMB that also should not exist. When you analyze the temperature pattern of the CMB at large angular scales, specifically the quadrupole and octupole moments, which correspond to the largest scale temperature variations, you find that they are aligned with each other. The axes of the quadrupole and octupole, two different scales of variation that should be randomly oriented in standard cosmology, point in the same direction. And that direction aligns, within measurement uncertainty, with the plane of our solar system. In standard cosmological theory, the CMB temperature variations should be statistically isotropic. No direction should be preferred. The quadrupole and octupole should be oriented randomly relative to each other and relative to any structure in our local neighborhood. The probability of the observed alignment occurring by chance in a standard inflationary universe is estimated at less than 1 in several thousand. A 2016 analysis compared isotropic and anisotropic cosmological models against both WMAP and Planck data and found no strong evidence for anisotropy in the data as a whole, suggesting the alignment might be a statistical artifact of the limited number of modes available at large angular scales rather than a genuine signal. The scientific debate has not been fully resolved. The significance of the axis of evil is this. If the alignment is real and not a statistical artifact, It implies either that the universe has a large-scale preferred direction, violating the cosmological principle of isotropy, or that some local structure in our solar neighborhood, which we should in principle be able to account for and subtract from the CMB maps, is creating a spurious alignment signal. Either possibility is uncomfortable. A universe with a preferred direction would require fundamental revision of the standard model. A contaminating local signal that has not been identified despite decades of careful analysis would imply that our CMB maps contain a systematic error we have not found. Beyond these specific anomalies, there is the general question of what lies behind the CMB wall itself. The universe before 380,000 years was causally accessible in the sense that events there shaped the initial conditions we see in the CMB. But those events cannot be observed directly through any electromagnetic radiation, because the universe was opaque. The only direct observational window into that era would come from gravitational waves or neutrinos produced in the early universe, which would not have been scattered by the plasma the way photons were. Detecting a primordial gravitational wave background or a cosmic neutrino background would allow us to see, in some sense, through the wall of last scattering to events much closer to the Big Bang. Both are extraordinarily challenging observations. The primordial gravitational wave background from inflation, if it exists, would imprint a specific polarization pattern on the CMB, called B-mode polarization, and several current and planned experiments are searching for it. The Simons Observatory, the CMB, S4 experiment, and the planned Lightbird satellite are all designed in part to detect or constrain this signal. A detection would be one of the most important measurements in the history of cosmology. Absence of detection would constrain models of inflation. The CMB is simultaneously our clearest view of the early universe, and an opaque barrier beyond which we cannot see. It shows us the universe at a specific moment with extraordinary clarity, but it hides everything before that moment. And within what it shows us, it contains anomalies that hint at something strange just beyond the edge of our understanding, cold spots and preferred axes that might be telling us something about what the universe is hiding in the oldest light it has ever emitted. Part 6. Black Holes and the Information Paradox. In 1974, Stephen Hawking published a calculation that shocked the physics community and has never been fully resolved in the 50 years since. He showed that black holes, which by their very definition should emit nothing, should in fact emit radiation. Quantum mechanics, applied to the region just outside the event horizon, predicted that particle-antiparticle pairs created by the vacuum would sometimes result in one particle falling into the black hole while the other escaped. Over time, this radiation would carry away energy and cause the black hole to slowly evaporate. The radiation itself, what we now call Hawking radiation, has a specific character. It is thermal. It looks like the radiation from a perfectly black body at a temperature inversely proportional to the mass of the black hole. A solar mass black hole has a Hawking temperature of about 60 billionths of a Kelvin, fantastically cold and utterly undetectable against the 725 Kelvin background of the CMB. Only the smallest black holes would be warm enough to produce detectable Hawking radiation, and we do not know if such small black holes exist. No Hawking radiation has been directly observed, but the existence of Hawking radiation, if you take quantum mechanics seriously, implies something deeply troubling. If a black hole can evaporate, then the information about everything that fell into it has a problem. Everything that falls into a black hole has a quantum state. Every particle has definite properties encoded in its wave function, its momentum, its spin, its entanglement relationships with other particles. Quantum mechanics, at its core, insists that quantum information is conserved. The universe does not delete information. The state of a system at any time determines its state at any other time, at least in principle. This is called unitarity. But Hawking's calculation suggested that the radiation emitted as a black hole evaporates is purely thermal. It does not carry the information about what fell in. When the black hole completely evaporates, that information is simply gone. Not hidden somewhere, not encoded in subtle correlations that we haven't yet detected. Destroyed. Lost forever. That violates unitarity, which is one of the most fundamental principles in quantum mechanics. This is the black hole information paradox. It is not a paradox in the casual sense of something that sounds contradictory. It is a precise mathematical conflict between two extraordinarily well-tested theories of physics, quantum mechanics and general relativity. Both of them work. Both of them make predictions that have been confirmed to extraordinary precision, and in the specific case of black hole evaporation, they make predictions that cannot simultaneously be true. Various resolutions have been proposed over the decades. One is that information is somehow encoded in subtle correlations in the Hawking radiation, correlations that look thermal on the surface but actually carry quantum information in an extremely scrambled form. This would require that the Hawking radiation is not exactly thermal, that there are departures from thermality that encode the quantum state of everything that ever fell into the black hole. No mechanism for this encoding has been convincingly identified, but a calculation called the Page curve, crisply derived by Don Page in 1993, shows mathematically that if unitarity is to be preserved, the information must start leaking out in the radiation by the time the black hole has evaporated roughly half its entropy. This Page time is an extremely long time for large black holes, and the mechanism that would accomplish the information leakage has remained unclear. A more radical proposal is the firewall, introduced in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, a paper that became known by their initials as AMPS. The AMPS argument showed that if you require the Hawking radiation to be unitary, carrying information out of the black hole, then an infalling observer would encounter a wall of high-energy radiation at the event horizon. The smooth, unremarkable crossing of the horizon, predicted by general relativity, would be replaced by an instantaneous destruction of anything approaching the horizon. The event horizon would be a firewall. This is disturbing because the equivalence principle, one of the foundation stones of general relativity, predicts that an infalling observer should not be able to detect the event horizon. For a sufficiently large black hole, the tidal forces at the horizon are negligible, and an observer falling in should feel nothing unusual as they cross it. The firewall hypothesis says that the horizon is actually a violent wall of fire, which directly contradicts the equivalence principle. The equivalence principle and unitarity cannot both be exactly right at the event horizon. Something has to give. The most interesting recent development comes from calculations involving what are called quantum extremal surfaces and entanglement islands. In 2019, several independent research groups showed that using the tools of holography and entanglement entropy, applying ideas from the AD-CFT correspondence, a deep result connecting gravity theories in curved spaces to quantum field theories on flat boundaries. You can reproduce the Page curve for an evaporating black hole. The calculation suggests that information is not permanently lost. But the mechanism involves the geometry of spacetime inside the black hole becoming relevant in a subtle way to the entropy accounting of the Hawking radiation outside, which requires taking seriously the possibility that regions inside the black hole are in some sense also accessible from outside it through quantum entanglement. This is deeply strange territory. The suggestion is that the interior of a black hole is not simply inaccessible after the event horizon forms, but is in some quantum mechanical sense entangled with, and perhaps encoded in, the radiation outside. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, goes even further, suggesting that entanglement between quantum systems is geometrically equivalent to Einstein-Rosen bridges, wormholes connecting different regions of spacetime. Under this picture, the interior of an evaporating black hole is connected through quantum geometry to the outgoing Hawking radiation, and the information is preserved not by being encoded in local properties of each photon, but by being distributed across global geometric structures that span the inside and outside simultaneously. None of this has been experimentally confirmed. The scales involved are so extreme, and the mathematical structures so abstract, that direct experimental tests in the near future are not feasible. What is experimentally clear is that black holes exist, that they consume matter and appear to destroy information from the perspective of outside observers, and that the theoretical resolution of what actually happens to that information remains one of the most active and contentious research areas in all of physics. Black holes also hide something else, something more immediate and only slightly less mysterious: their interiors. Once you cross the event horizon of a black hole, the laws of physics as we understand them describe a trajectory toward a singularity. A singularity is a point, or a ring for rotating black holes, where the density becomes infinite, the curvature of space-time becomes infinite, and the equations of general relativity break down completely, returning values that have no physical meaning. The singularity is the place where general relativity stops working. What actually happens at a singularity? Nobody knows. General relativity says the curvature diverges to infinity, which is the theory's way of admitting it has no idea. Most physicists believe that a complete theory of quantum gravity would replace the singularity with something finite and physical, some structure at the Planck scale that behaves in ways our current theories cannot describe. String theory's fuzzball proposals suggest that the singularity is replaced by a compact object made of stringy matter whose surface radiates like a normal body without forming an information-destroying horizon. Loop quantum gravity predicts that the singularity is replaced by a high-density bounce point where the collapsing matter reaches a maximum density and begins to expand again, perhaps creating a new region of space-time on the other side. But all of these are theoretical proposals without observational support. The interior of a black hole is perfectly, absolutely, permanently hidden from outside observers. Nothing that happens inside the event horizon can affect anything outside it. No signal, no photon, no gravitational wave, no quantum correlation can carry information about the singularity outward through the horizon. The inside of a black hole is the most private place in the universe. It hides its own physics from the rest of reality. The universe has arranged its most extreme concentrations of mass in structures that simultaneously hide their interiors from observation and challenge the completeness of our physical theories at their surfaces. Black holes are not just objects. They are the universe's mechanisms for concealing its own deepest physics. Part 7. Neutrinos, the particles that barely exist. Right now, as you read or listen to this, approximately 100 trillion neutrinos are passing through your body every second. Every second. Not occasionally. Not when conditions are right. Constantly. Always. 100 trillion per second, streaming through you as if you were not there at all. You feel nothing. Neutrinos are the most abundant matter particles in the universe. There are roughly 336 neutrinos per cubic centimeter in the universe, left over from the Big Bang, a relic neutrino background, analogous to the cosmic microwave background, but made of particles rather than photons. They fill every cubic centimeter of space throughout the observable universe. And yet they interact so weakly with ordinary matter that detecting them requires enormous detectors buried deep underground to shield them from the cosmic ray backgrounds that would overwhelm the signal. Even then, a detector containing thousands of tons of material might record only a handful of neutrino interactions per day. A neutrino can travel through a light year of lead and have only a 50-50 chance of interacting with anything. Neutrinos are produced in enormous quantities by nuclear reactions. The Sun produces approximately 2 × 10 to the 38th neutrinos per second as a byproduct of the fusion reactions in its core. Those neutrinos travel through the entire mass of the Sun, from the core to the surface, in about 2 seconds. For comparison, a photon produced in the solar core takes roughly 100,000 years to random walk its way to the surface, bouncing off electrons and ions in the dense plasma. The neutrinos pass through all of that without even noticing. Nuclear reactors produce neutrinos, specifically electron antineutrinos, in prodigious quantities. Supernovae produce more neutrinos in 10 seconds than the Sun will produce in its entire 10 billion year lifetime. The supernova SN 1987A, which occurred in the Large Magellanic Cloud about 160,000 light-years away, produced a burst of neutrinos that was detected simultaneously at 3 different underground detectors around the world. 24 individual neutrino events were recorded across those detectors, out of the 10 to the power of 58 neutrinos that the event produced. That detection ratio gives you a sense of the neutrinos' commitment to not interacting. For most of the 20th century, neutrinos were believed to be massless. The standard model of particle physics, as originally formulated, predicted massless neutrinos. This prediction was convenient because it was consistent with the observations at the time and avoided certain theoretical complications. Then, in 1998, the Super Kamiokande experiment in Japan published a result that changed everything. By studying neutrinos produced when cosmic rays hit the upper atmosphere, the experiment found that muon neutrinos were disappearing in a way that depended on how far they had traveled. Neutrinos produced in the atmosphere above the detector traveled downward through just a few tens of kilometers and arrived mostly intact. Neutrinos produced on the opposite side of the Earth traveled upward through the entire planet, more than 12,000 kilometers, and a significant fraction of them had converted into tau neutrinos along the way. This process, called neutrino oscillation, is only possible if neutrinos have mass. A massless particle cannot oscillate between types. The standard model needed to be revised. The discovery that neutrinos have mass won Takaaki Kajita of Super Kamiokande and Arthur MacDonald of the Sudbury Neutrino Observatory, which solved the separate solar neutrino problem, the 2015 Nobel Prize in Physics. Neutrinos have mass, but the mass is extraordinarily small. The sum of the masses of all three neutrino types is constrained to be less than about 0.12 electron volts, less than 1/millionth of the mass of an electron, which is itself one of the lightest known particles. Neutrinos are almost massless. They are the lightest massive particles known to science. There are three types, or flavors, of neutrinos: electron, muon, and tau, one corresponding to each of the three charged leptons. There are also three corresponding mass states, called mass 1, mass 2, and mass 3. The confusing feature of neutrino physics is that the flavor states and the mass states are not identical. Each flavor is a quantum mechanical mixture of all three mass states, mixed in specific proportions, characterized by three mixing angles. As a neutrino propagates through space, the different mass components travel at slightly different speeds because their masses are slightly different. And this causes the quantum state to rotate, so that after some distance, a neutrino that started as an electron neutrino has a probability of being detected as a muon or tau neutrino. This is oscillation. The details of the mixing, specifically the values of the three mixing angles and the differences in the squared masses of the three types, determine how neutrinos oscillate. Two of the three mixing angles have been measured with good precision. The third mixing angle, called theta 1,3, was measured in 2012 by the Diabei experiment in China. The differences in squared masses are known. What is not yet known is the mass ordering. Whether the heaviest mass state is mass 3 and the two lighter ones are mass 1 and mass 2, the so-called normal ordering, or whether mass 3 is the lightest and mass 1 and mass 2 are the heavier pair, the inverted ordering. This is called the neutrino mass hierarchy problem, and its solution is one of the primary goals of current neutrino physics. In August 2025, the Jiangmen Underground Neutrino Observatory, JUNO, located deep beneath the mountains of southern China, was declared operational after more than a decade of construction. JUNO is the largest liquid scintillator neutrino detector ever built, using a 20-kiloton sphere of transparent scintillator liquid surrounded by more than 40,000 photomultiplier tubes. It is designed specifically to measure tiny distortions in the energy spectrum of reactor antineutrinos that would allow determination of the mass hierarchy. Even before its official data taking began, antineutrino events were recorded that matched predictions. The neutrino mass hierarchy problem is not just a technical detail. The ordering of neutrino masses matters for understanding how neutrinos shaped the large-scale structure of the universe in the early epochs after the Big Bang, how matter came to dominate over antimatter through a process called leptogenesis, and whether the neutrino is its own antiparticle, what physicists call a Majorana fermion, or whether the neutrino and antineutrino are distinct particles, as in the case of electrons and positrons. In October 2025, the T2K experiment in Japan and the NOVA experiment in the United States published the first joint analysis of their combined neutrino oscillation data in the journal Nature. The results offered some of the most precise measurements of neutrino oscillation parameters to date and provided tentative hints about the mass ordering and about the possible violation of charge parity symmetry in neutrinos. CP violation in the lepton sector, meaning that neutrinos and antineutrinos oscillate differently, could be the mechanism that generated the matter-antimatter asymmetry that allowed the universe to exist. If in the early universe, processes involving neutrinos and antineutrinos occurred at slightly different rates due to CP violation, the result could have been a small excess of matter over antimatter, exactly the excess that allows everything we see to exist. This is not speculative in the way dark matter candidates are speculative. The mechanism is physically motivated and mathematically coherent. What we do not yet know is whether the CP violation in neutrinos is large enough and of the right form to explain the observed matter-antimatter asymmetry. The ongoing neutrino oscillation experiments are designed in part to answer exactly this question. The cosmic neutrino background deserves its own moment of reflection. The relic neutrinos that fill the universe, produced in the first second after the Big Bang when the universe was hot enough for weak interactions to keep neutrinos in thermal equilibrium, decoupled from ordinary matter at roughly 1 second after the Big Bang when the universe had cooled to about 10 billion Kelvin. Since then, those neutrinos have been streaming freely through the universe, their momenta redshifted by the expansion of space, just as the CMB photons' momenta have been, to a current temperature of about 1.95 Kelvin. They are everywhere, now and always, passing through you at close to the speed of light, utterly invisible to any current detector. In 2025, a paper by the European Space Agency's Euclid Space Telescope team, analyzing the large-scale structure of the universe mapped by Euclid, announced the first cosmological measurement of neutrino mass oscillations through their effects on the cosmic web. The gravitational influence of neutrinos on structure formation, measurable through subtle distortions in how galaxies cluster, provided a new window on neutrino mass from a completely different direction than laboratory experiments. This kind of cosmological neutrino measurement will become increasingly precise as Euclid and future large-scale structure surveys accumulate data. Neutrinos represent the universe's most successful strategy for moving information around without being noticed. They are produced in the cores of stars, in the hearts of supernovae, in the first second of the universe's existence, and in the cores of nuclear reactors, and they carry that information outward through any amount of intervening material without being stopped, scattered, or absorbed. The universe uses them as messengers that pass through walls, and almost all of those messages go forever unread, because detecting them requires instruments whose sheer scale borders on the absurd. Part 8. The Great Voids. Here is something that might make you feel the scale of the universe differently than statistics ever could. There is a region of space centered in the direction of the constellation Boötes that spans approximately 330 million light-years. That is a sphere so large that our closest galactic neighbor, the Andromeda Galaxy at 2.5 million light-years, would cover only about 1% of its diameter, and throughout that enormous volume, there are approximately 60 galaxies. In a normal region of the same volume, you would expect to find roughly 2,000 galaxies. The Boötes void, discovered by Robert Kirshner and his colleagues in 1981 during a survey of galactic redshifts, is one of the largest known empty regions in the universe. The 60 or so galaxies that have been found within it are not distributed evenly across the void. They are clustered in a tube-shaped region running through the middle, as if the void had been carved out around them, and they found themselves stranded in the resulting emptiness. Astronomer Greg Aldering once described the scale of the Boötes void this way: if the Milky Way had been located at the center of the Boötes void, we would not have discovered other galaxies until the 1960s. For context, Edwin Hubble first identified galaxies beyond the Milky Way in the 1920s. In the Boötes void, the nearest other galaxy would be so far away that our telescopes throughout most of the 20th century would not have been powerful enough to see it. An intelligent civilization in the center of the Boötes void would grow up thinking that their galaxy was the entire universe, and they would be unable to correct that impression until they had built technology we only achieved within living memory. Voids are not simply regions where galaxies haven't formed yet. They are regions that have been actively evacuated. The large-scale structure of the universe forms through gravitational dynamics that simultaneously cause matter to accumulate in sheets, filaments, and clusters, while pulling matter away from the regions in between, leaving them progressively emptier over cosmic time. The cosmic web is not just the structure of the matter that exists. It is equally defined by the voids that contain almost none, and the voids occupy most of the volume of the universe. Estimates suggest that voids account for roughly 80% of the total volume of the observable universe. The luminous cosmic web, the glowing filaments and clusters of galaxies that look so spectacular in visualizations, is actually the minority in terms of space. The universe is, by volume, predominantly empty. This emptiness is not simply absence. Voids have detectable effects on the light that passes through them. As a photon travels through a void, the gravitational potential it is, crossing changes, because the universe is expanding, and the void is a region of lower than average density. Through a process called the integrated Sachs-Wolf effect, light traveling through voids loses a small amount of energy compared to what it would lose traveling through average or overdense regions. This means that the cosmic microwave background is, very subtly, cooler in the directions of large voids, because the CMB photons traveling from those directions have crossed voids on their journey to us. This effect connects directly to the cold spot anomaly discussed earlier. The Eridanus supervoid, a particularly large and deep void discovered at about 6 to 10 billion light-years in the direction of the constellation Eridanus, has been proposed as a partial explanation for the CMB cold spot. The void would cause CMB photons traveling through it to lose energy, producing a cold region in the microwave sky. The problem is that the Eridanus supervoid is probably not large enough and empty enough to produce the full depth of the cold spot observed. The explanation may be partial rather than complete, and the remainder of the cold spot's anomaly may require additional physics. The Eridanus supervoid, if it exists as currently proposed, is vast. Preliminary estimates suggest it may span roughly 500 million light-years or more, making it one of the largest individual structures identified in the observable universe. At 6 to 10 billion light-years distance, it is also extraordinarily remote. Its existence is inferred from the distribution of galaxies in that region and from the CMB signal, rather than from direct three-dimensional mapping, and its properties remain uncertain. Then there is the KBC void, also called the local hole, the void within which our own galaxy sits. The Milky Way is not located in one of the dense filaments or clusters of the cosmic web. We are in a somewhat underdense region, a void that extends roughly several hundred million light-years in our vicinity. This local underdensity has a potential contribution to the Hubble tension, because if we happen to be inside a void, local measurements of the expansion rate might be systematically higher than the global average due to the enhanced outflow of matter from the underdense region. Whether the KBC void is deep enough and large enough to account for the full Hubble tension is a matter of ongoing research and debate. Voids also serve as natural laboratories for testing theories of gravity and dark energy. In voids, the gravitational dynamics are simpler than in the dense regions where galaxy clusters form. There is less material, fewer interactions, and the evolution of the void can, in principle, be calculated with greater precision. The geometry of voids, how round they are, how quickly they expand, how their walls evolve over cosmic signal, depends sensitively on the properties of dark energy and on any modifications to general relativity that might be operating at large scales. Current and future galaxy surveys, including DESI and Euclid, include void analyses as a significant component of their dark energy and gravity science programs. There is something philosophically striking about the role of voids in cosmic structure. We tend to think of structure as the positive thing, the presence of matter, the accumulation of galaxies. But the voids are not just the gaps between structures. The voids are themselves structural elements. The cosmic web is defined as much by its empty interiors as by its luminous walls. The voids push outward, their sub-average gravity causing surrounding matter to flow toward the walls rather than toward any central concentration within the void. This outflow shapes the filaments, contributing to the overall architecture of the cosmic web in a way that would not emerge from the accumulation of matter alone. The universe is mostly empty. Not empty in the way that the solar system is mostly empty, where the emptiness is a vacuum punctuated by the occasional planet or asteroid. Empty in a deeper, more persistent, more deliberate sense. Enormous volumes of space that contain so few galaxies that an entire civilization could arise and achieve spaceflight. and never have direct evidence of cosmological scales of structure. The universe has arranged its matter in thin, luminous threads and walls surrounding vast spheres of almost nothing. And in those spheres of almost nothing, the universe has hidden some of its most subtle and informative signals about what dark energy is doing and how gravity behaves at the largest scales. Part 9. The antimatter that vanished. At the moment of the Big Bang, or more precisely in the first fraction of a second afterward, when the universe was hot enough for particle-antiparticle pairs to be spontaneously created from pure energy, the universe should have made matter and antimatter in exactly equal amounts. That is what the known laws of physics predict. For every quark that appeared, an antiquark. For every electron, a positron. For every proton, an antiproton. Perfect balance. Perfect symmetry. If that symmetry had been perfect, the universe's subsequent history would have been extremely brief and extremely boring. As the universe cooled, the quarks and antiquarks would have found each other and annihilated. The electrons and positrons would have found each other and annihilated. Everything would have annihilated. The universe would have been left as a bath of photons and perhaps neutrinos, expanding and cooling into an unstructured sea of radiation, with no atoms, no molecules, no chemistry, no planets, no stars, no galaxies, and absolutely no observers of any kind. You exist because something went wrong with that symmetry. For reasons that physics does not yet fully explain, the universe produced slightly more matter than antimatter in those first moments. The excess was tiny. For every billion quarks and billion antiquarks, there was one extra quark. 1 billion plus 1 versus 1 billion. The quarks and antiquarks annihilated. The quarks and antiquarks canceled perfectly, and the one extra quark was left over. Multiplied across the staggering number of particles produced in the Big Bang, that 1 in a billion excess was enough to produce all the ordinary matter in the observable universe. Every atom in your body is a survivor of that annihilation. You are the surplus. This asymmetry between matter and antimatter has a name: baryogenesis, or more specifically, baryon asymmetry. Baryons are the class of particles that includes protons and neutrons, the building blocks of atomic nuclei. The universe today contains approximately 10 to the power of 78 baryons, and effectively 0 antibaryons in the observable volume. The annihilation left an overwhelmingly matter-dominated universe. In 1967, the Soviet physicist Andrei Sakharov, who would later become famous as a dissident and human rights advocate, identified 3 conditions that any explanation of the matter-antimatter asymmetry must satisfy. Known as the Sakharov conditions, they are: first, baryon number violation, meaning there must exist physical processes that can change the number of baryons in the universe, creating an excess where there was none. Second, C and CP symmetry violation, meaning the laws of physics must behave differently for matter and antimatter, so that the baryon number violating processes create more matter than antimatter. And third, departure from thermal equilibrium, meaning these processes must occur at a time when the universe is not in perfect thermodynamic equilibrium, otherwise forward and reverse processes would cancel out any asymmetry. The standard model of particle physics contains all 3 of Sakharov's conditions in principle. It includes processes that violate baryon number, called sphaleron processes, which are active at high temperatures like those of the early universe. It includes CP violation, observed in the weak decay of certain particles like neutral kaons and B mesons. And the early universe passed through phase transitions, such as the electro-weak symmetry breaking, that represented departures from equilibrium. The problem is magnitude. The CP violation measured in the standard model, the degree to which matter and antimatter behave asymmetrically in particle decays, is far too small to account for the observed baryon asymmetry. If you run the calculation with only the standard model's CP violation, the excess matter produced is many orders of magnitude smaller than what we actually observe. The standard model's CP violation is a real effect, confirmed in multiple experiments, but it is far too tiny to explain why the universe is matter-dominated rather than radiation-dominated. This means there must be new physics beyond the standard model that provides additional sources of CP violation large enough to produce the observed asymmetry. What this new physics is remains unknown. Neutrinos have emerged as the most compelling current candidate for providing the missing CP violation. The process of leptogenesis proposes that in the early universe, heavy relatives of the known neutrinos, called right-handed or sterile neutrinos, decayed through processes that violated lepton number and CP symmetry, producing more leptons than antileptons. These leptonic asymmetries were then converted into a baryonic asymmetry through the sphaleron processes active in the hot early universe. If leptogenesis is correct, the observed matter-antimatter asymmetry is ultimately a neutrino physics phenomenon, a legacy of the CP violation in the lepton sector that was amplified in the hot early universe. The exciting implication is that measuring CP violation in the oscillations of ordinary neutrinos, the kind accessible to current and planned experiments like T2K, NOVA, DUNE, and Hyper-Kamiokande, could provide clues about the magnitude and form of the CP violation in the early universe that set up the asymmetry. The October 2025 joint T2K and NOVA analysis, published in Nature, showed hints of CP violation in neutrino oscillations, with antineutrinos and neutrinos appearing to oscillate somewhat differently. The results were not conclusive enough to claim a discovery, but the direction of the hint was consistent with what leptogenesis would predict. The experiments are still running, collecting more data, and the question is expected to become clearer as statistics improve. Antimatter itself, meanwhile, has been extensively studied in particle accelerators and in dedicated experiments. The ALPHA experiment at CERN has trapped antihydrogen atoms, the antimatter equivalent of the simplest atom, and measured their properties with increasing precision over the past decade. By comparing the spectral lines of antihydrogen with those of ordinary hydrogen, physicists test whether the laws of atomic physics are identical for matter and antimatter. So far, the measurements are consistent with perfect symmetry between hydrogen and antihydrogen at the level of sensitivity achieved. The BASE experiment at CERN has measured the magnetic moment of the antiproton with extraordinary precision and compared it with the proton, finding no detectable difference at the current level of measurement. The ALPHA-G experiment measured the gravitational acceleration of antihydrogen in 2023 and found it falls downward, as expected, rather than upward, ruling out some exotic theoretical possibilities that anti-gravity was responsible for the matter-antimatter asymmetry. What all of this tells us is that antimatter, where it exists, behaves almost identically to matter under all conditions that have been tested. The asymmetry that allows the universe to exist is not something that can be simply explained by antimatter falling up or by some gross difference in the properties of particles and antiparticles. It is a subtle, microscopic difference in the rates of certain weak interaction processes, a difference large enough to produce a 1 in a billion excess, but small enough that 50 years of particle physics measurements have only recently begun to see clear evidence of it in neutrino behavior. The universe made a choice at the beginning. It decided, for reasons that physics does not yet fully explain, to be matter rather than nothing. The antimatter that was its symmetric counterpart was annihilated into radiation, and the small excess of matter that remained went on to build everything that has ever existed. We are the remainder after the greatest annihilation event in cosmic history. Where did the antimatter go? Into photons. The cosmic microwave background is, in a real and literal sense, the light of annihilation. Every photon in that background radiation was produced by a particle meeting its antiparticle and vanishing into pure energy in the first minutes after the Big Bang. The light that fills the universe is the record of the destruction that preceded creation. And the antimatter itself, having converted fully into that light, is gone. The universe has hidden it in the most complete way possible. It no longer exists. Part 10. Beyond the observable edge. Consider what we mean when we say observable universe. The term is precise. It does not mean the universe we have actually observed. It means the universe we could in principle observe, given unlimited observational resources, the entire volume of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. You might expect, therefore, that the observable universe extends about 13.8 billion light-years in every direction. That would be true if the universe were not expanding. Because the universe is expanding, And because the expansion means that the matter that emitted the most distant light we can detect was much closer to us when that light was emitted than it is now, the actual radius of the observable universe is considerably larger. The proper distance to the edge of the observable universe, accounting for the expansion of space over the time the light has been traveling, is approximately 46.5 billion light-years. The full diameter of the observable universe is roughly 93 billion light-years. Outside that sphere, nothing. Not nothing in the sense of empty space, but nothing in the sense of zero information. Not one photon, not one gravitational wave, not one neutrino. No signal of any kind has had time to reach us from beyond that boundary. The regions beyond it are not part of our observable universe in any operational sense. They could contain anything. They could contain nothing. We have absolutely no data, and the boundary is not static. Two things are happening simultaneously that affect what is and is not in our observable universe over time. First, as time passes and the universe gets older, light from more distant regions has had more time to reach us. The observable universe grows over time, incorporating regions that were previously beyond our particle horizon. In principle, an observer watching over cosmic time would gradually see more and more of the universe as light from progressively more distant regions arrived. But second, and here is the disturbing part, the accelerating expansion of the universe means that galaxies currently near the edge of the observable universe are receding from us at velocities close to or exceeding the speed of light in terms of the recession due to space expansion itself. For galaxies beyond what is called the Hubble radius, currently about 14 billion light-years, the expansion of space is already carrying them away from us faster than light can cross the gap. This does not violate special relativity, because the galaxies are not moving through space faster than light. It is space itself that is expanding, but the effect is the same. Light emitted by a galaxy beyond the Hubble radius right now will never reach us. The future of the observable universe is therefore one of progressive isolation. Galaxies currently at the edge of our observable volume, the ones whose ancient light is just now arriving, will at some future time emit light that we will never see. As the expansion accelerates under the influence of dark energy, more and more galaxies will cross the cosmological event horizon and enter a zone of permanent invisibility. The light they are emitting today is on its way to us, but the light they will emit in the far future will never arrive. In the very long run, billions and then trillions of years from now, every galaxy outside our local group will have receded beyond the event horizon. The night sky will go dark. The cosmic microwave background will have redshifted to energies too low to detect. Future observers, if any existed, would live in what appears to be an island universe, a small collection of bound galaxies, surrounded by empty, dark, cold space, stretching to infinity in every direction, with no evidence in the observable sky that anything else exists. The universe as a whole will have the same amount of matter and radiation that it has today. But the observable universe will be isolated from almost all of it. This is not speculation. It is the mathematically rigorous consequence of dark energy causing an exhilarating expansion. The universe is actively, in real time, reducing the amount of itself that is accessible to any given observer. We happen to live at a time when the observable universe is still rich with structure and filled with the light of billions of galaxies. But that window is closing, cosmologically speaking. Even if the closing takes billions of years, beyond the particle horizon, in the unobservable universe, what might exist? If the universe is infinite, or even if it is merely much larger than the observable portion, then everything that exists within the observable universe exists out there as well, simply beyond our reach. Every type of star, every type of galaxy, every possible chemical composition, and if the universe is large enough, then by the same statistics that govern large numbers, every possible arrangement of matter that is not forbidden by the laws of physics exists somewhere out there, including, in principle, other regions that look almost exactly like our observable universe, other arrangements that look nothing like it. The inflationary theory of cosmology, which proposes a brief period of extraordinary exponential expansion in the first tiny fraction of a second of the universe's existence, predicts that the universe is far larger than the observable portion, potentially by a factor so enormous it makes the ratio between the observable universe and an atom seem small. Inflation can, in principle, produce a universe so vast that, even if the whole is finite, the unobservable portion dwarfs the observable one in any ratio you care to name. Some versions of inflation, so-called eternal inflation, predict that the inflation never truly stopped everywhere, but continues in most of the universe, with localized regions like ours where the inflation ended and normal expansion began. In eternal inflation, our observable universe is one bubble of settled space-time in a larger, still inflating substrate. Other bubbles exist, other regions where inflation ended at different times, possibly with different physical constants, different strengths of forces, different particle masses. These other bubble universes would be separated from us by regions of still inflating space-time through which we could never travel or communicate. This is the multiverse hypothesis in its inflationary form. It is a genuine theoretical consequence of a well-motivated inflationary model, not a science fiction concept. But it is also, by construction, permanently unverifiable in any direct sense. No signal from another bubble universe can reach us. No observation we could make inside our observable universe could distinguish between a multiverse and a single universe that simply happens to have initial conditions consistent with our model. The multiverse might be real. It might not be. Physics has no way to distinguish. The edges of the observable universe hide, at minimum, an enormous amount of perfectly ordinary universe that looks like what we see but is inaccessible. And possibly, if inflation's more extreme versions are correct, an ensemble of bubble universes with varying properties in a substrate that will never stop expanding. The universe has arranged its most extreme inaccessibility, not behind walls of matter or electromagnetic opacity, but behind the geometry of space-time itself. The particle horizon is the most absolute hiding place in physics. Nothing penetrates it in either direction. There is something clarifying about this specific form of hiding. The zone of avoidance hides things we might one day see better with improved instruments or from different vantage points. Dark matter might one day be detected in a more sensitive experiment. The interior of black holes might one day be partially understood through quantum gravitational calculations. But the unobservable universe is not hidden by any of these incidental barriers. It is hidden by the finite age of the universe and the geometry of expanding space-time. No instrument improvement changes it. No theoretical advance removes the barrier. The unobservable universe simply is, permanently and structurally, hidden from ours. The universe has drawn some curtains with erasable ink. The cosmological event horizon is drawn in something permanent. Part 11. Final synthesis. A universe in hiding. We have traveled a long way, from the gravitational rivers pulling hundreds of thousands of galaxies toward a hidden concentration of mass behind the galactic plane, to the invisible scaffolding of dark matter that outweighs everything we can see by 5 to 1. From the accelerating expansion driven by something we cannot directly detect or explain from first principles, to the ancient light that carries within it anomalies that hint at something strange in the oldest moments of the universe. From black holes that consume information and hide their own interiors behind boundaries of absolute concealment, to the ghost particles that pass through everything and carry messages from stellar cores we could never otherwise see. From the great voids that occupy most of the universe's volume while contributing almost nothing to its light, to the vanished antimatter whose annihilation is written into the background radiation filling all of space. From the edges of what light has had time to reach us, to the permanent darkness beyond the cosmological horizon, what connects all of these? Is there a theme, a common thread, or is the universe simply hiding things for different and unrelated reasons at different scales? There is a thread, and it is worth pulling. The universe hides things when the tools we have for seeing are mismatched with the nature of what exists. Our eyes evolved to detect electromagnetic radiation in the visible band because that is what the sun produces in abundance, and because surfaces and objects at ordinary temperatures interact with light. Our physics for most of its history was built around electromagnetic phenomena because that was what we could observe. We built a civilization of observation on the assumption that if something exists, it eventually glows or reflects or absorbs light in some detectable way. The universe does not respect that assumption. It contains dominant forms of matter and energy that do not interact electromagnetically. It builds its most important gravitational structures out of material that produces no photons and absorbs none. It encodes its deepest physics inside objects whose most consequential physics happens below the quantum scale or behind geometric barriers that no electromagnetic signal can cross. It distributes 100 trillion messengers per second through your body, carrying information from the cores of stars, and it arranges those messengers to slip through the best detectors we have built as if they were not there. The universe is not deliberately hiding things in the way that a person might hide something. It has no intentions, but it is organized in a way that consistently and persistently exceeds the reach of our most natural observational tools. The things it hides are not peripheral or marginal. They are, repeatedly and embarrassingly, the most important things. The most abundant form of matter is invisible. The dominant component of cosmic energy is undetectable by any direct means. The processes that allowed matter to exist at all happened in a regime of energy and temperature that no conceivable future accelerator will reproduce. What does this mean for the project of understanding the universe? It means that the history of cosmology and physics has been, repeatedly, a history of discovering that what we thought was most of the picture was actually a small and unrepresentative fraction of it. The Earth at the center of the cosmos gave way to a sun at the center, and then to a sun at the edge of a galaxy, and then to a galaxy in a local group, and then to a local group in a supercluster, and then to a supercluster, as a minority in a universe mostly made of something else entirely. Each discovery of what the universe is hiding has required abandoning not just a specific model, but an entire framework of assumptions about what kind of thing the universe fundamentally is. The dark matter and dark energy problems are not anomalies in an otherwise complete picture. They are the picture. They are telling us that the physics we understand applies to a small and perhaps unrepresentative corner of what exists. The information paradox is not a technical detail to be cleaned up. It is a sign that two of our best theories of nature are fundamentally incompatible in one of the universe's most extreme environments, and that the resolution will require something we have not yet invented. The neutrino mysteries, the matter-antimatter asymmetry, the CMB anomalies, the cosmological constant problem, these are not loose ends in an otherwise finished tapestry. They are the load-bearing walls of a structure whose foundation we have not yet fully identified. There is something honest and clarifying about accepting this situation directly. The universe is mostly hidden. What we can see is a small, electromagnetically active minority that floats inside a much larger, much stranger, almost entirely invisible structure. We have learned enough to know the shape and rough composition of that structure through indirect means. We have not learned enough to identify its most basic components or explain why it has the properties it has. This is not failure, it is progress. A century ago, we did not know that other galaxies existed. We did not know the universe was expanding. We did not know there was a cosmic microwave background. We did not know that black holes existed as real astrophysical objects rather than mathematical curiosities. We did not know that neutrinos had mass. We did not know that the expansion of the universe was accelerating. Every one of those discoveries was a revelation about something the universe had been hiding, revealed by the patient accumulation of better observations and better theoretical tools. The things the universe is hiding now are harder. They require detectors buried kilometers underground, satellites mapping the oldest light in the universe to 1 part in a million, enormous underground spheres filled with transparent liquid, watching for the faintest whisper of a particle interaction, radio telescopes scanning through the obscuring plane of the galaxy to find the structures hidden behind it, sky surveys mapping millions of galaxies to find the subtle distortions in their clustering caused by dark energy and neutrino masses. The universe does not give up its secrets easily. It hides them behind the plane of the galaxy, behind the electromagnetic silence of dark matter, behind the geometric curtain of the cosmological horizon, behind the infinite density of the singularity, behind the quantum scrambling of black hole evaporation, behind the almost nothing mass of ghost particles. It hides them behind the barrier of the last scattering surface, behind the annihilation of its own antimatter, behind the empty volumes where galaxies decided not to form. But it does not hide them perfectly. It leaves fingerprints. The flat rotation curves of galaxies, the lensing signatures in the cosmic web, the peculiar velocities of hundreds of thousands of galaxies, all pointing in the same direction, the spectral lines of hydrogen atoms broadcasting the quantum state of the universe at 1.42 gigahertz from every corner of space, the 24 neutrino events that arrived from a dying star, 160,000 light-years away, and told us the death was happening before our optical telescopes had even opened their shutters. The universe hides most of itself, but it is not perfectly silent. It leaves, in the parts we can see, the imprints of everything it is trying to conceal. And the ongoing project of reading those imprints, of learning to see the invisible through its effects on the visible, is one of the most extraordinary things that has ever happened in the history of matter, that became conscious of itself and started asking questions. Every time we think we understand what the universe is, it turns out we have been looking at a small fraction of it. Every discovery about what it hides has been followed by the discovery that there is more hiding still. The darkness behind the light is deeper than the light. The undetected outweighs the detected. The hidden outnumbers the visible. And somewhere in the gap between what we can see and what exists, between the 5% we understand and the 95% we don't, between the edge of the observable universe and the infinite darkness beyond it, there are answers to questions we have not yet learned to ask. The universe has been hiding things since before there were eyes to see. It will keep hiding them, in the zone of avoidance and in the cores of black holes and in the silence of the neutrino background and in the darkness of the cosmological night that is slowly, galaxy by galaxy, falling over everything that exists. But we keep looking. That is the most remarkable thing in all of this. Against the darkness of an almost entirely invisible universe, something small and temporary, made of the 5% majority, looked up and started counting what it could not see. If this took you somewhere you didn't expect to go tonight, leave a like. It genuinely helps this reach more people who would want to see it. And if you are new here, subscribe, because we are going to keep following these questions wherever they lead, all the way to the edges of what can possibly be known. There is so much more hiding out there. We are just getting started. Part 12. The first second what the universe did before it let us see. The cosmic microwave background, the oldest light in the universe, is a record of the universe at 380,000 years old. Before that, the universe was opaque. The plasma was too hot and too dense for photons to travel freely. So that wall of last scattering, that moment when atoms formed and light was finally released, is the absolute hard limit on how far back in time electromagnetic observations can take us. But the universe existed before 380,000 years. It existed for the entirety of those 380,000 years in complete electromagnetic secrecy. And in that hidden interval, the most consequential events in cosmic history occurred. The first second of the universe is perhaps the most densely packed chapter in the history of anything. More happened in that first second. More different kinds of physics, more phase transitions, more particle creations and annihilations, more symmetry breakings and symmetry restorations than in all the time that followed. The universe in its first second went through energy scales that dwarf anything achievable in any particle accelerator that exists or could reasonably be built. The Large Hadron Collider at CERN, the most powerful particle accelerator ever constructed, achieves collision energies of about 13 tera-electron volts. The temperature of the universe 1 microsecond after the Big Bang corresponds to energies of about 300 mega-electron volts per particle. 1 microsecond after the beginning, the universe was at energy scales that our best accelerators only begin to approach. At 1 second after the Big Bang, the temperature was about 10 billion Kelvin, roughly 500 times hotter than the center of the Sunday. The universe was a dense mixture of quarks, gluons, electrons, positrons, muons, antimuons, neutrinos, antineutrinos, and photons, all in near-perfect thermal equilibrium, colliding and annihilating and recreating so rapidly that the composition was determined by the temperature alone. At about 1 microsecond, the temperature dropped enough for quarks and gluons to condense into protons and neutrons through a process called the QCD phase transition, the moment when quantum chromodynamics, the theory of the strong nuclear force, caused free quarks to become permanently confined inside hadrons. Before this moment, quarks roamed freely in a quark-gluon plasma, After it, every quark was locked inside a proton, neutron, or other hadron. Within the first few minutes after the Big Bang nucleosynthesis occurred, the process by which free protons and neutrons combined into the first atomic nuclei. Helium, deuterium, lithium, and very small amounts of beryllium were all synthesized in this window. The abundance of these light elements, measured today in old stars and in primordial gas clouds that have not been significantly processed by stellar nucleosynthesis, serves as a diagnostic of conditions in those first few minutes with extraordinary precision. The predicted abundances from Big Bang nucleosynthesis match the observed abundances at a level that constitutes one of the strongest confirmations of the hot Big Bang model. But before all of this, before nucleosynthesis, and before the QCD phase transition, the universe went through what is called the electroweak phase transition. At temperatures above about 100 giga-electron volts, the electromagnetic force and the weak nuclear force, which appear as distinct forces at low energies, are unified into a single electroweak force. The Higgs field has an expectation value of 0. Particles, including the W and Z bosons that mediate the weak force, have no mass. The universe is symmetric with respect to the electroweak symmetry group. As the universe cools through this temperature, the Higgs field undergoes a phase transition, acquiring a non-zero expectation value, and the symmetry is spontaneously broken. The W and Z bosons acquire their large masses. The electromagnetic and weak forces separate into the distinct forces we observe today. This phase transition, if it proceeded through what is called a first-order transition, meaning it proceeded through bubble nucleation, similar to how bubbles of steam form in boiling water, could have produced departures from thermal equilibrium and conditions favorable for baryogenesis, the generation of the matter-antimatter asymmetry. In the standard model, the electroweak phase transition is actually a smooth crossover rather than a sharp first-order transition, meaning the conditions for generating a large matter-antimatter asymmetry are not met. This is one of the reasons the standard model cannot explain baryogenesis by itself. Extensions of the standard model that make the transition first order are actively studied. Before the electroweak phase transition, there is the electroweak epoch, and before that, the gut epoch, when the strong, weak, and electromagnetic forces may have been unified into a single grand unified theory force at temperatures above roughly 10 to the 28 Kelvin. Direct observational tests of physics at GUT energy scales are essentially impossible with any foreseeable technology. The LHC operates at scales roughly 10 to the 13 times lower than GUT scales. And before the GUT epoch is the Planck epoch, the first 10 to the negative 43 seconds, the so-called Planck time, when the energy density was so high that quantum gravitational effects dominated, and all four forces, including gravity, were presumably unified. Physics at the Planck scale is the domain of whatever theory of quantum gravity will eventually be established. No experimental evidence from this epoch is directly accessible by any method currently known. In between the Planck epoch and the electroweak phase transition is the inflationary epoch, proposed to have occurred somewhere between 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang. Inflation proposes that the universe underwent a period of exponential expansion, driven by the energy of a scalar field called the inflaton. During inflation, the observable universe expanded from a region far smaller than a proton to roughly the size of a marble in an extraordinary short time. The exact timing and mechanism of inflation are not known. What inflation accomplishes is remarkable. It explains why the CMB is so uniform in temperature across regions that, without inflation, would never have been in causal contact with each other. It explains why the universe appears spatially flat, because any initial curvature would have been stretched away by the exponential expansion. It produces a nearly scale-invariant spectrum of density perturbations from quantum fluctuations of the inflaton field, which matches the observed CMB power spectrum with remarkable precision. And it predicts, in many models, a background of primordial gravitational waves that would leave a distinctive imprint in the polarization of the CMB. The gravitational wave imprint of inflation is perhaps the most eagerly sought observational target in cosmology. Its detection would be a direct probe of physics at energy scales 10 orders of magnitude above the LHC. Its non-detection constrains the energy scale at which inflation occurred and the particular shape of the inflaton potential. The search for primordial B-mode polarization in the CMB, the specific pattern of polarization that gravitational waves would produce, is one of the primary objectives of the Simons Observatory and the planned CMB S4 experiment. Everything that happened in the universe's first 380,000 years is hidden from direct electromagnetic observation. We infer it from theoretical models, from the light element abundances produced in nucleosynthesis, from the precise pattern of CMB temperature fluctuations, from the particle physics experiments that test the forces in particles relevant to the early universe, and from the gravitational wave observations that may, if we are fortunate and our models are correct, eventually let us hear the first moments of creation. The universe's first chapter was written in a language we cannot directly read. It left its fingerprints in the universe we can observe, and decoding those fingerprints is the work of cosmology. But the text itself, the actual events, remains hidden behind a wall of hot plasma that the physics of atomic recombination drew at 380,000 years and has not moved since. Part 13. Zone of avoidance, a sky with a hole in it. There is a band across the sky that astronomers have historically tried not to look at, not because there is nothing there, but because everything they tried to see through it was obscured by the very galaxy they were living in. The galactic plane, the thick equatorial disk of the Milky Way, absorbs and scatters visible light so efficiently that optical observations in that direction see, effectively, the interior of a fog. Not the vastness of the universe beyond, just the local fog of our own stellar neighborhood. This region is called the zone of avoidance, and it covers roughly 20% of the sky. For most of the history of extragalactic astronomy, the zone of avoidance was simply a blank on the map. Catalogs of galaxies showed a clear band running around the sky, where no galaxies were recorded, not because there were none, but because we could not see them. The universe's structure in that direction was simply unknown. This was cosmologically consequential because, as it turned out, some of the most important structures in our local universe are located precisely in or near the zone of avoidance. The Great Attractor, the gravitational focal point pulling hundreds of thousands of galaxies, including our own, sits almost exactly at the heart of this blind spot. The Norma cluster, one of the most massive nearby galaxy clusters, was identified through its X-ray emission rather than its optical light. The full extent of the large-scale structures behind the galactic plane remained speculative for decades. Astronomers developed strategies for peering through the obscuration. At radio wavelengths, the interstellar dust that blocks optical light is largely transparent. The 2-1 centimeter hydrogen line, which hydrogen atoms emit as their electrons spin, flips from parallel to anti-parallel with the proton's spin at a frequency of 1.42 GHz, passes through the galactic dust with minimal absorption. Radio surveys of the zone of avoidance have been conducted since the 1970s, mapping the distribution of galaxies through their hydrogen emission rather than their starlight. Near-infrared observations also penetrate the dust more effectively than visible light, since the longer wavelengths are less susceptible to scattering. Near-infrared surveys conducted in the 1990s and 2000s began to reveal the galaxy distribution within the zone of avoidance in increasing detail, identifying thousands of previously unknown galaxies hidden behind the galactic plane. The Sarao Meerkat Telescope in South Africa, one of the most sensitive radio telescopes in the world and a precursor to the Square Kilometre Array, has in recent years been conducting deep surveys of the southern zone of avoidance with unprecedented sensitivity. The CF4++ catalog of galaxy peculiar velocities, used in the 2025 Vela supercluster analysis discussed earlier, incorporated over 2,000 interferometric hydrogen observations from Meerkat, specifically targeting the innermost 3-degree-wide strip of the southern zone of avoidance, regions that had never been probed at such depth before. The result was the most detailed view ever obtained of the structures immediately behind the galactic plane. What was revealed was dramatic. The Vela supercluster, a massive concentration of galaxies at about 800 million light-years, had been identified in earlier surveys, but its full extent and mass were not clear. The new Meerkat observations confirmed it as a dominant mass concentration rivaling the Shapley concentration, the most massive structure in the nearby universe previously known. The zone of avoidance had been hiding one of the most massive nearby structures in the universe. This is a recurring theme in the zone of avoidance story. Every time new observational technology allowed astronomers to look more deeply into the galactic plane, they found significant structures that had been invisible. The question of what lies immediately behind the center of our galaxy, the most obscured direction of all, remains partially open. The density of stars, gas, and dust toward the galactic center is so extreme that even radio surveys struggle to separate the extragalactic signal from the overwhelming foreground. The very heart of the zone of avoidance is the most opaque region in the sky, and it happens to be the direction from which our best measurements suggest significant contributions to the local gravitational flow. The zone of avoidance will eventually be mapped completely. As radio telescope sensitivity continues to improve, and as surveys reach deeper into the third dimension through galaxy redshift measurements rather than just angular positions. But for now, it represents a genuinely blind spot in our knowledge of the local universe, one where the instruments of modern astronomy have been only partially effective, and where significant surprises may still be hiding. The zone of avoidance is not the universe hiding things from us on purpose. It is us living inside the very structure we are trying to see, like trying to make a map of a city while standing inside one of the buildings. Our position within the Milky Way's disk is simultaneously what makes the galaxy our home and what makes the universe's most interesting local directions, the hardest ones to examine. Part 14. The quantum foam and what spacetime hides at the smallest scale. Everything we have discussed so far in this exploration of the universe's hidden things has been macroscopic, hidden structures at the scale of hundreds of millions of light years, hidden particles at the scale of atoms and nuclei, hidden information behind event horizons. But there is another kind of hiding that operates at the absolute smallest possible scale, the Planck scale. And what is hidden there may be the deepest secret of all. The Planck length is approximately 1.6 times 10 to the minus 35 meters. This is a distance so small that it makes an atomic nucleus at about 10 to the minus 15 meters look enormous. Specifically, the ratio of the Planck length to the size of a proton is roughly the same as the ratio of a proton size to a human fingernail. And then, you would need to apply that same ratio again and again to get to the Planck scale. It is not just a small distance. It is a distance at which, according to our best current theoretical understanding, the concept of smooth, continuous space breaks down. John Wheeler, the physicist who coined the terms black hole and wormhole, and who was one of the 20th century's most creative thinkers about the deep structure of spacetime, proposed the concept of quantum foam in the 1950s. Wheeler's idea was that at the Planck scale, the Heisenberg uncertainty principle, applied to the energy and geometry of spacetime itself, would make spacetime turbulent, fluctuating, foamy. The smooth, continuous spacetime we experience at macroscopic scales would be, at the deepest level, a seething froth of quantum geometric fluctuations, with tiny topological structures, microscopic wormholes and black holes, constantly appearing and disappearing on timescales of the Planck time, roughly 5.4 times 10 to the minus 44 seconds. This is not an established, experimentally confirmed picture. No observation has yet directly detected quantum foam. No experiment can probe the Planck scale with any instrument that exists or is currently foreseeable. But the concept follows from combining the basic principles of quantum mechanics with general relativity, and it represents the current best guess of many theoretical physicists about what spacetime looks like at its finest scale. If quantum foam is real, then at every point in what we perceive as smooth, empty space, at the scale smaller than any measurement we can make, there is a complex, dynamic, fluctuating geometric structure. The apparent smoothness of space is an emergent, macroscopic averaging over this microscopic chaos. Just as the smooth flow of water in a river looks nothing like the jostling thermal motion of individual water molecules, smooth spacetime looks nothing like the Planck scale quantum geometry that underlies it. The implications of quantum foam for what the universe hides are profound. If the smooth geometric concepts of general relativity, the curvature of space-time, the smooth definition of distances and angles and volumes, break down at the Planck scale, then the physical laws we use to describe everything from particle physics to cosmology are effective theories, valid approximations at the scales we can probe, but emergent features of a deeper structure that looks nothing like them. The black hole singularity is the most immediate physical consequence of this. A singularity, in classical general relativity, is a point of infinite density and curvature. But infinity is unphysical. It means the theory has broken down. Whatever actually happens at the center of a black hole presumably involves Planck-scale physics, quantum gravitational effects that replace the infinite curvature with something finite and physically meaningful. We do not know what that replacement looks like because we do not have a complete and experimentally validated theory of quantum gravity. The Big Bang singularity is the same story at cosmic scale. The beginning of the universe, as described in classical general relativity, extrapolated backward to the earliest times, produces a singular point of infinite density. This singularity is almost certainly not physical. The actual initial conditions of the universe, whatever they were, involve quantum gravitational physics at or near the Planck scale, and the classical equations break down there. What the universe looked like at the Planck time, or before the Planck time, or whether the concept of before has any meaning at those scales, is simply unknown. The Hartle-Hawking no-boundary proposal, a quantum cosmological framework developed by James Hartle and Stephen Hawking, suggests that the universe has no boundary in time, that it began in a quantum state that has no singular beginning point, but instead has a smooth quantum geometry in which the time direction smoothly becomes a spatial direction near the beginning. The way the surface of the Earth has no edge at the geographic South Pole, despite being finite. In this picture, asking what happened before the Big Bang is like asking what is south of the South Pole. The question has no answer, not because something is hidden, but because the concept of before does not apply. Time itself emerges from a quantum geometric state that does not contain time in the same way our current universe does. These ideas are mathematically interesting and physically motivated, but not experimentally tested. They represent the current frontier of theoretical attempts to understand what the universe hides at its smallest and earliest scales. What the Planck scale and the quantum nature of space-time hide from us is, in a certain sense, the deepest layer of the universe's hidden architecture. Not hidden because it is far away, or because it does not emit light, but hidden because it is the substrate from which everything else is built. The quantum foam, if it is real, is what everything sits on. It is the texture of existence at its finest resolution, and it is completely inaccessible to any measurement we know how to make. Part 15. The hidden signals we are only beginning to hear. For most of the history of astronomy, we were limited to a single messenger, light, electromagnetic radiation of various wavelengths. Radio waves from pulsars and galactic hydrogen, infrared from dusty galaxies, visible light from stellar surfaces, ultraviolet from hot gas, X-rays from accretion disks, gamma rays from explosive events. The entire electromagnetic spectrum, from the longest radio waves to the shortest gamma rays, was the window through which we observed the universe. On the 14th of September 2015, a different kind of window opened. At 5:51 inches the morning Eastern Time, the two gravitational wave detectors of the LIGO experiment recorded a signal that lasted about 0.2 of a second. The signal was a brief rising chirp, a frequency increasing from about 35 Hz to about 150 Hz, corresponding to two black holes, spiraling together and merging. The merger had occurred approximately 1.3 billion light-years away. The gravitational waves produced by that event had been traveling through the universe at the speed of light for 1.3 billion years, and they passed through the Earth, compressing and stretching space by a fractional amount of about 10 to the minus 21, distorting the 4-kilometer arms of the LIGO detector by a distance smaller than 1,000th the diameter of a proton. We detected it. That detection opened a new observational window on the universe. A window through which electromagnetic dark events could be seen. Black hole mergers, which produce no electromagnetic radiation in most circumstances, are observable through gravitational waves. Neutron star mergers, observed in gravitational waves in August 2017 and simultaneously confirmed by electromagnetic observatories around the world, in what is called GW 170817, produce both gravitational waves and electromagnetic radiation, allowing for multi-messenger observations that constrain the equation of state of extremely dense nuclear matter and measure the speed of gravitational waves to within 1 part in 10 to the 15 of the speed of light. The gravitational wave window reveals things the electromagnetic window cannot. It sees through the gas and dust that obscures optical observations. It reaches into the dark interior of dense stellar environments. It can, in principle, detect the primordial gravitational wave background from inflation, if such a background exists at detectable amplitude. The current and planned gravitational wave detectors represent an accelerating program of window opening. LIGO and Virgo continue to operate and improve. The Kagra detector in Japan has joined the network. The Einstein telescope, a proposed underground triangular detector in Europe with 10-kilometer arms, and the Cosmic Explorer, a proposed 40-kilometer arm detector in the United States, would have sensitivity dramatically exceeding current instruments and could detect black hole mergers throughout most of the observable universe. The space-based LISA mission, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will detect gravitational waves at lower frequencies than ground-based detectors, opening sensitivity to supermassive black hole mergers, the inspiral of stellar mass compact objects into supermassive black holes, and potentially the stochastic gravitational wave background from the early universe. Meanwhile, the neutrino window offers yet another view of what the electromagnetic sky hides. The IceCube Neutrino Observatory, buried in a cubic kilometer of Antarctic ice at the South Pole, has been detecting high-energy cosmic neutrinos since 2013. These are neutrinos produced by the most energetic processes in the universe: supermassive black holes consuming matter, gamma-ray bursts, supernovae, and other extreme events. By tracking the directions from which high-energy neutrinos arrive, IceCube can identify sources of cosmic ray acceleration that are hidden from gamma-ray telescopes by intervening material that absorbs the gamma rays. In 2022, IceCube published strong evidence that the galaxy NGC 1068, also known as Messier 77, is a source of high-energy neutrinos. NGC 1068 is a ciphered galaxy with an active galactic nucleus, a supermassive black hole consuming material at its center, surrounded by dense, absorbing material. The gamma-ray emission from this black hole is suppressed by the absorption, making it relatively faint in gamma rays. But the neutrinos, being insensitive to the absorbing material, escape freely and arrive at IceCube with full strength. The neutrino signal tells us about the energetic processes happening inside the absorbing material around the black hole, processes that are completely hidden from electromagnetic observation. In August 2025, the Juno detector in China began operations with its primary goal of determining the neutrino mass hierarchy. But Juno will also serve as a supernova neutrino observatory. When the next galactic supernova occurs, Juno will record tens of thousands of neutrino events from it, providing a high statistics view of the neutrino burst from the collapsing stellar core. The neutrinos from a supernova escape hours before the electromagnetic signal, because they propagate freely through the stellar envelope, while the optical light takes hours to reach the stellar surface. In the case of SN 1987A, the 24 neutrino events were recorded before the first optical detection. A galactic supernova, detected by Juno and IceCube, simultaneously with optical and gravitational wave telescopes, would be one of the richest astronomical events ever observed. We are in the early stages of building a multi-messenger observatory for the universe, a network of instruments sensitive to gravitational waves, neutrinos, cosmic rays, and the full electromagnetic spectrum, each revealing aspects of the universe that are hidden from the others. The universe has been broadcasting information through all of these channels for the entire age of the cosmos. For most of that time, we had only one receiver. We are only now building the others. What will those new channels reveal? Gravitational wave astronomy is expected to detect the stochastic background of merging compact objects throughout the universe's history, building a picture of the merger rate and mass function of black holes across cosmic time. It may detect cosmic strings, topological defects from early universe phase transitions, whose gravitational wave signature would be a direct probe of physics at unimaginably high energies. It may, if inflation produced gravitational waves at the right amplitude, directly measure the energy scale of inflation. Neutrino astronomy will reveal the inner workings of the most powerful engines in the universe, the supermassive black holes driving active galactic nuclei, hidden behind absorbing material that electromagnetic telescopes cannot penetrate. It will measure the diffuse supernova neutrino background, the accumulated neutrinos from every core collapse supernova throughout cosmic history, which encodes the entire history of massive star formation in the universe. The universe has been hiding most of its activity from our electromagnetic telescopes. Not all of it, but most of it. The events that release the most energy, the merging of stellar mass black holes, the collapse of massive stars, the accretion of matter onto supermassive black holes behind absorbing dust and gas, the high-energy particle acceleration in relativistic jets, these events either produce no electromagnetic radiation at all, or produce it in forms that cannot escape the environments where the events occur. Multi-messenger astronomy is the systematic project of opening the windows through which these hidden events can finally be seen. If you have made it this far, if you've sat with these questions and followed them all the way to the edge of what we know and into the space beyond it, then you already understand something important about the universe. It is not a place that gives itself up easily. It rewards patience and careful attention and the willingness to stay with a difficult question long after the easy answers have been exhausted. Like this video if this took you somewhere you didn't expect to go. Subscribe if you want to keep going. We will follow these questions wherever they lead, and drop a comment telling us where in the world you are watching from and what time it is there. This channel reaches every corner of the planet and every hour of the day, and we love knowing that. The universe is hiding things. We are going to keep looking. Appendix: the deep questions behind the hidden things. There is a question that runs beneath every section of this exploration, a question so fundamental that most scientific papers do not ask it directly, because it sits outside the normal boundaries of what physics considers answerable. The question is this: why is the universe set up in a way that hides so much of itself from observation? This is not an accident of cosmic placement, though our position inside the Milky Way's disk does create the zone of avoidance. The hiding goes much deeper than local obscuration. The dominant components of the universe, dark matter and dark energy, do not interact electromagnetically, not because of some unfortunate accident of our observation strategy, but because that is simply how those components are built. Their electromagnetic silence is a property of their nature, not their location. The universe made the choice, if we can call it that, to construct the majority of its content out of material that does not produce light. We arrived as electromagnetic creatures in an overwhelmingly non-electromagnetic universe, and we brought telescopes. Consider what it would mean for the nature of science if the universe had been constructed differently. If dark matter were ordinary baryonic matter, perhaps in the form of large quantities of black holes or very cold gas clouds, it would interact electromagnetically, and we would have detected it long ago. If dark energy were a form of hot gas rather than a property of empty space, it would glow, and we would see it. The universe would be essentially fully visible, fully mappable through electromagnetic means, and the picture of cosmic structure we built from those observations would be accurate and complete. The history of cosmology would have been enormously simpler. Instead, we live in a universe where the accurate picture requires modes of observation we only developed in the last few decades: gravitational wave detection, high-energy neutrino astronomy, careful statistical analyses of galaxy velocities rather than direct imaging, indirect inference of dark matter through gravitational effects, and where the most important phenomena operate at energy scales we cannot directly probe with particle accelerators. Whether this is coincidence or whether it reflects something deep about the nature of physics is itself an open question. The anthropic reasoning would suggest that we should not be surprised to find ourselves in a universe complex enough to generate observers like us. And a universe with the observed balance of dark matter and dark energy turns out to have properties: the right amount of structure formation, the right expansion history, the right conditions for star formation and planetary chemistry that are necessary for our existence. A universe with wildly different proportions of dark matter and dark energy would likely not produce observers capable of asking the question. But this reasoning, while plausible, does not predict the specific values of the dark matter and dark energy densities. It explains at most why we should not be surprised to find ourselves here rather than in a universe incompatible with life. It does not tell us why the universe is predominantly non-electromagnetic, why the cosmological constant has the specific tiny value it has, why matter and antimatter are so nearly equal with only a 1 in a billion excess, why neutrinos are so nearly massless. The particular parameters of our universe still demand explanation beyond the anthropic reasoning. The cosmological constant problem, again, sits at the center of this issue. The vacuum of quantum field theory, empty space itself, should have an enormous energy density due to zero-point quantum fluctuations of all the quantum fields that fill it. When you calculate this contribution from first principles, the result is about 10 to the 120 times larger than the observed cosmological constant. Something is canceling that enormous quantum contribution down to near zero with extraordinary precision, leaving only the tiny residual that drives the observed acceleration of expansion. No known mechanism performs this cancellation. The fact that the residual is not exactly zero, that the cosmological constant is tiny but non-zero, makes the cancellation even more puzzling, because a perfect cancellation to exactly zero could potentially reflect some unknown symmetry, while a cancellation to a very small non-zero value seems arbitrary. This is sometimes called the fine-tuning problem, or the coincidence problem. The density of dark energy is comparable, in order of magnitude, to the density of matter in the universe today. The matter density decreases as the universe expands, because the matter is spread over a larger volume. The dark energy density is constant, or nearly so. At different epochs in cosmic history, the ratio between these densities was very different. In the early universe, matter dominated, and dark energy was negligible. In the distant future, dark energy will dominate entirely, and matter will be negligible. We happen to live at a cosmic epoch when the two densities are within an order of magnitude of each other. Is this a coincidence? Did we arrive on the scene at a cosmically special moment when matter and dark energy happen to be comparable? Or is there a physical reason why observers like us can only exist at epochs when the two densities are comparable? This is the cosmological coincidence problem, distinct from the cosmological constant problem, and it too lacks a satisfying resolution. The hidden things in the universe are not just scientifically challenging, they are philosophically challenging. They raise questions about whether our current theoretical framework is the right one for understanding what exists, questions about fine-tuning, and whether physical parameters can be explained from deeper principles or are simply given, questions about the nature of initial conditions, and whether a scientific theory of those conditions is even in principle possible. The biggest hidden thing in the universe may not be any specific structure or particle. It may be the deeper framework of physics that would explain why the universe has the parameters it has, why dark matter exists and what it is, why the cosmological constant is so small and non-zero, why matter dominates over antimatter, why neutrinos are so light but not massless. A theory that answered all these questions would not just be an extension of current physics. It would be a different kind of physics, one that addresses the origin of parameters rather than just their consequences. We do not have that theory. We are building toward it, incrementally, through the patient accumulation of measurements and the careful development of theoretical frameworks that match them. The hidden things are the clues, the dark matter halos, the flat rotation curves, the acceleration of expansion, the CMB anomalies, the neutrino masses, the matter-antimatter asymmetry. Each of these is a message from the deeper physics, a fingerprint of something we have not yet fully grasped. Reading those messages is the work of the coming decades and centuries, and each message, when properly decoded, will likely reveal another layer of hiding below it, another set of questions that open beneath the ones we have answered, another darkness that the growing circle of knowledge reveals at its advancing edge. The universe keeps its secrets well, but it leaves enough fingerprints, enough anomalous signals and gravitational whispers and quantum signatures that the project of finding them has never been more productive, never better equipped, and never more likely to make the kinds of discoveries that rewrite the foundations of our understanding. The darkness is deep, but so is the light we bring to it. Every question we have followed in this exploration, from the gravity river of the Great Attractor to the quantum foam of the Planck scale, from the antiparticle ghosts of the Big Bang to the permanent isolation imposed by the cosmological event horizon, is a question about the edge between the known and the unknown. And that edge is moving, slowly, unevenly, sometimes in surprising directions, but always moving. The observable has always been smaller than the real, and the real has always been stranger than we thought. That is not a reason for despair. It is the engine of discovery. The universe hides things precisely as well as our understanding needs to improve in order to find them. We are, in this sense, in a universe perfectly calibrated to be explored by minds that build telescopes and particle detectors and mathematical frameworks and refuse to be satisfied with incomplete answers. Keep looking up. Keep following the questions. The universe is still hiding most of itself, and that means the most important discoveries in the history of human understanding are almost certainly still ahead. If you made it to the end of this, thank you. Genuinely. This is the kind of content that takes a long time to research and write, and the fact that you are here for all of it means everything. Like this video if it gave you something to think about. Subscribe if you want more of this kind of deep dive. And leave a comment with where in the world you are watching from. We will see you in the next one. Part 16. Magnetic Fields. The universe's invisible architecture in the visible world. Dark matter and dark energy are the most famous of the universe's invisible constituents, but they are not alone. There is another invisible structure, one that threads through the visible matter of the universe and yet is routinely underappreciated even within the scientific community. Cosmic magnetic fields. Vast, coherent magnetic structures that permeate galaxies, galaxy clusters, and possibly the cosmic filaments of the large-scale web itself. Magnetic fields are not exotic or mysterious in the way dark matter is. We understand the physics of magnetic fields thoroughly. Maxwell's equations, written in the 1860s, describe them completely in the classical regime. Quantum electrodynamics extends that description into the quantum world. Magnetohydrodynamics describes how magnetic fields interact with conducting fluids, from stellar plasmas to the hot gas in galaxy clusters. We know what magnetic fields are. What we do not know is how the universe acquired the large-scale magnetic fields we observe, or how coherent those fields are at the largest scales. Galaxies are permeated by magnetic fields with typical strengths of a few microgauss, roughly 1,000,000 times weaker than a refrigerator magnet, but organized on scales of thousands of light years. In the Milky Way, the field is roughly aligned with the spiral arm structure of the galaxy, winding in organized patterns across tens of thousands of light years. In other spiral galaxies observed with radio telescopes, the magnetic field structures are even more dramatically organized, with coherent spiral patterns that mirror the optical structure of the galaxy. Galaxy clusters contain magnetic fields threading the hot intracluster medium, the diffuse ionized gas filling the space between the cluster's member galaxies. These fields have been detected through their effect on radio waves passing through the cluster, specifically through a phenomenon called Faraday rotation, in which a magnetic field along the line of sight rotates the plane of polarization of linearly polarized radio emission. By measuring how much the polarization angle has rotated, astronomers can infer the strength and orientation of the magnetic field between the source and the observer. The puzzle is where these large-scale magnetic fields came from. Generating a magnetic field from nothing requires breaking the initial symmetry of a purely matter-filled space. In a perfectly homogeneous, initially field-free universe, there is no mechanism in standard physics that spontaneously generates a coherent magnetic field without some seed. The standard picture is that tiny seed fields were generated very early in the universe's history, possibly during inflation or during the electroweak phase transition, and were subsequently amplified by dynamo processes operating within galaxies and galaxy clusters over billions of years. The problem is that the theoretically predicted seed fields from early universe processes are typically extremely weak, far weaker than what is required to explain the observed galactic and cluster fields through straightforward amplification. The amplification mechanisms in galaxies involve the differential rotation of the galactic disk, turbulence in the interstellar medium, and the interaction of the rotating disk with any initial seed field. Theoretical models of these processes can, in principle, amplify a weak seed field to observed strengths over cosmological timescales, but the details are complex and uncertain. What has recently become particularly compelling is evidence for magnetic fields in the cosmic voids. If magnetic fields exist in the largely empty voids between cosmic filaments and clusters, they cannot have been generated by astrophysical processes within galaxies or clusters, because those processes are confined to the regions of visible structure. Void magnetic fields would have to be primordial, generated in the early universe before structure formation had organized matter into galaxies and clusters. Evidence for void magnetic fields comes from observations of gamma-ray blazars, the most luminous persistent sources of gamma rays in the universe, which are supermassive black holes in distant galaxies with relativistic jets pointed toward us. When a very high-energy gamma ray travels through empty space toward us, it should produce electron-positron pairs by interacting with the diffuse background of optical and infrared photons that fill the universe. These pairs should then interact with the same background photons to produce a secondary gamma ray signal at lower energies, a cascade that should arrive at our telescopes as a halo around the blazar. The absence of such halos, observed in multiple blazars by the Fermi Gamma Ray Space Telescope and ground-based Cherenkov telescopes, is interpreted by many physicists as evidence that an intergalactic magnetic field is deflecting the charged electron-positron pairs enough that the secondary gamma rays arrive, spread out over a larger angle than can be resolved, effectively making the secondary emission too diffuse to detect. The magnitude of the deflection can be used to set a lower limit on the intergalactic magnetic field strength. These limits suggest that even the voids, the most empty regions of the cosmic web, contain magnetic fields with strengths of at least 10 to the minus 15 Gauss, 1 femtogauss. This is fantastically weak, barely detectable by any current means, but it is not zero. And for fields to exist in voids, they must have been generated primordially, before voids existed as distinct structures. They must have been present in the early universe, seeded during some phase transition or other energetic event at high temperature, and they have survived to the present, diluted by the expansion of space and the growth of the void regions, but detectable through their effects on the most energetic photons we observe. If primordial magnetic fields exist throughout the universe, they have influenced the formation of structure in ways that are not fully accounted for in standard cosmological simulations, most of which do not include magnetic fields at all. They may have affected the formation of the first stars. They may have seeded the galactic dynamos that produce the observed galactic fields more efficiently than the tiny fields that quantum processes would generate. They may have left detectable imprints in the cosmic microwave background. They are another layer of invisible architecture, threaded through the visible universe, shaped by processes in the early universe that we only partially understand, and doing things to the structure we observe that we are only beginning to quantify. The story of cosmic magnetic fields is in many ways a microcosm of the broader story of the universe's hidden things. We observe the effects. We know the effects are real. The detailed understanding of the origin and cosmic history of what is producing those effects remains genuinely, productively incomplete. Part 17. Gravitational waves as a new language of the hidden universe. When the first gravitational wave detection, GW150914, was announced on the 11th of February 2016, it was described as a triumph of human ingenuity and experimental physics. The detectors had been sensitive enough to detect a change in the length of a 4-kilometer interferometer arm by a distance of 1,000th the diameter of a proton. The engineering involved was extraordinary. Mirrors polished to atomic smoothness, seismic isolation systems that removed ground vibrations to a level far below the sensitivity threshold, quantum optics techniques to reduce the noise from the quantum nature of light itself. The measurement was a genuine tour de force. But what makes gravitational waves important for the story of what the universe hides is not the engineering, it is the physics of what they carry. A gravitational wave is a ripple in the curvature of space-time itself, propagating outward from an accelerating mass at the speed of light. Two black holes spiraling around each other and eventually merging generate a rapidly increasing gravitational wave signal, a chirp, that encodes information about their masses, their orbital dynamics, the moment of merger, and the properties of the final merged black hole. None of that information is carried in any electromagnetic signal. For a binary black hole merger, there is no electromagnetic counterpart at all, because the black holes carry no charge and are surrounded by no significant infalling material. The only way to observe these events is through gravitational waves. In the years since GW 150914, the LIGO, Virgo, and KGRA network of gravitational wave detectors has observed nearly 100 gravitational wave events, dozens of binary black hole mergers, several binary neutron star mergers, and at least one neutron star black hole merger. Each event reveals the masses and spins of the merging objects, the distance to the event, and the orientation of the orbit relative to Earth. This is a census of compact object mergers in the universe across billions of years of look-back time, a census that would be completely inaccessible through any other observational means. The gravitational wave events reveal things that were previously completely hidden. The masses of the merging black holes in many of the detected events fell in ranges that were theoretically unexpected. Several events involved black holes with masses between about 50 and 100 solar masses, a range called the pair instability blast gap, where stellar evolution theory predicted black holes should not form because stars in that mass range would be entirely disrupted by electron-positron pair instability before they could collapse. The observation of merging black holes in this mass range implies either that our stellar evolution models are wrong in important ways, or that these are second-generation black holes formed from the mergers of smaller black holes in dense stellar environments like globular clusters, where merger remnants can accumulate. These discrepancies are not problems in a negative sense. They are discoveries. The hidden merger history of black holes throughout the universe, revealed through gravitational waves, is telling us things about stellar evolution, the formation of compact objects, and the dynamics of dense stellar environments that optical and X-ray observations were never able to reveal. Looking further into the future, the space-based LISA mission will open the millihertz gravitational wave band, sensitive to the mergers of supermassive black holes at the centers of distant galaxies. Supermassive black hole mergers are thought to occur when two galaxies merge, and their central black holes sink to the center through a combination of dynamical friction and gravitational wave emission. The gravitational wave signal from a merger between 2 billion solar mass black holes at cosmological distances would be detectable by LISA across essentially the entire observable universe. These events are the most energetic in the universe, potentially converting several percent of the merged object's mass into gravitational wave energy in a few hours, but they have never been directly observed because they produce no reliable electromagnetic counterpart. LISA will change that. It will observe the supermassive black hole merger history of the universe, revealing how galaxies built their central black holes through repeated mergers across cosmic time. This history is one of the most consequential hidden processes in galaxy formation and evolution, currently inferred only indirectly through the relationship between black hole mass and galaxy properties in the local universe. There is also the stochastic gravitational wave background, a diffuse background of gravitational waves from all the merging compact objects throughout cosmic history, unresolved into individual events, adding together into a noise background that LISA will measure statistically. This background encodes the integrated history of compact object formation and merging across the entire observable universe. And beyond the astrophysical component, there may be a cosmological component from processes in the early universe, phase transitions, cosmic strings, inflation itself, which would be a direct probe of physics at energy scales utterly inaccessible by any other means. The gravitational wave window on the universe is still in its early hours. We are hearing the universe speak a language it has been broadcasting since its first fraction of a second, a language that carries information about its hidden processes, its invisible mergers, its opaque early epochs. We have only just learned the first words of it. The full conversation is still ahead. Part 18, The Quiet Revolution in How We Think About Hidden Things. There is a philosophical shift happening in physics and cosmology, one that is less dramatic than any single discovery, but may ultimately be more significant than any of them. It is a shift in how scientists think about the relationship between what is observable and what is real. The traditional scientific attitude, sometimes called positivism or operationalism, holds that scientific statements should be verifiable in principle through observation or experiment. If a proposition cannot, even in principle, be tested by any observation, it is not a scientific proposition. This attitude has been enormously productive. It kept physics grounded in measurement when it might have drifted into unverifiable metaphysics. The prediction of the Higgs boson, the detection of gravitational waves, the imaging of a black hole's shadow, these are triumphs of the positivist approach. Theoretical prediction, experimental verification. But the universe is now presenting physics with situations where this clean division between theory and experiment is seriously strained. The multiverse, if eternal inflation is correct, contains regions that are causally disconnected from us and can never influence any observation we make. Yet it is a straightforward prediction of a well-motivated theory of the inflationary epoch. The interior of a black hole cannot communicate its physics to the outside, yet understanding what happens there requires a theory. The physics of the first Planck second cannot be observed, yet it sets the initial conditions for everything that followed. These situations have forced a more nuanced conversation about what it means for a physical theory to make contact with reality. Some theorists argue that if a theory makes testable predictions about the observable universe, the unverifiable predictions that follow from the same theory must also be taken seriously, even if those specific predictions cannot be directly tested. The string theory landscape, for example, predicts an astronomical number of possible vacuum states corresponding to different physics, most of which are unobservable, but the theory itself makes specific predictions about the properties of gravity and matter that could be tested by future measurements. Others argue that a theory that hides its most important content behind unverifiable predictions is not a fully scientific theory and should be treated with appropriate caution. The debate is genuine and ongoing. What is clear is that the universe's insistence on hiding things has forced physics into a more mature relationship with the distinction between what we know and what we believe, between what is confirmed and what is theoretically predicted, between what the data says and what the most compelling theoretical framework implies. The hidden things have not just expanded our scientific program, they have expanded our scientific epistemology, our understanding of what it means to know something about the universe. The history of science shows repeatedly that what was once thought to be permanently hidden turned out, with new instruments or new theoretical insight, to be accessible after all. The interior of the atom was thought inaccessible until Rutherford's scattering experiments revealed it. The structure of the sun's core was thought permanently hidden until solar neutrino detectors read the fusion reactions from 93 million miles away. The surface of the universe at 380,000 years was thought unobservable until the precision mapping of the CMB made it the best characterized object in cosmology. Each of these revealed what seemed like a fundamental limit to be a temporary technological limitation. There is no guarantee that today's limits are permanent. The hidden things we have explored in this video, the dark matter, the dark energy, the Planck scale physics, the unobservable universe beyond the event horizon, each of them may yield to approaches that we have not yet conceived. Some of them may not. The cosmological horizon is a different kind of limit than the opacity of the solar interior. But the track record of physics suggests that the appropriate attitude is neither despair at the hiddenness of the universe, nor overconfidence that all limits are temporary. It is patient, creative, carefully grounded attention to what the observations say and what they imply, combined with the imagination to propose new frameworks that might reveal what the current ones cannot see. The universe is hiding things. It has always been hiding things. The history of science is the history of coaxing the universe into revealing, one layer at a time, more of what it keeps concealed. Each revelation has been more surprising than the one before, and each has revealed a deeper hiding. There is no reason to think we have reached the last layer. Every generation of scientists has thought they were approaching the final picture, and every generation has been surprised. The next surprises are already hidden in the data we have, waiting for the right framework to make them visible. They are in the anomalies we have not yet fully explained, in the tensions between measurements that should agree, in the theoretical puzzles that have resisted every approach attempted so far. The universe is still hiding things. And somewhere, in the community of scientists working today, or among the students now learning physics for the first time, are the people who will find them. That is not a distant hope. It is an active, ongoing process, happening right now in underground laboratories and mountaintop observatories and computer clusters crunching the latest survey data and theoretical offices where someone is staring at an equation that doesn't quite work and thinking, for the first time, that the mismatch might be telling them something real. The darkness has depth, the questions have weight, the work is worth doing, and the universe, whatever it is hiding, is patient. It has been keeping its secrets for 13.8 billion years. It is not in a hurry, but we are. Thank you for being here. If this video reached you at 2 in the morning with the lights off, or on a lunch break, or on a long flight, or in some quiet moment when you needed something real to think about, then this was made for you. Leave a like, leave a comment telling us where you are in the world, and subscribe, because we are going to keep chasing these questions for as long as there are questions worth chasing, which is to say, forever. A final note on scale and wonder. Before we close, take a moment to sit with what we have covered, not as a list of facts, but as a single, continuous picture. You are a temporary arrangement of ordinary matter, the 5% minority, sitting on a rocky planet orbiting a middle-aged star at the edge of a barred spiral galaxy, made of 400 billion stars, inside a gravitational basin called Laniakea that is slowly flowing toward a hidden mass concentration, embedded in a cosmic web of filaments and voids where roughly 80% of the volume contains almost nothing, in a universe that is 95% invisible, accelerating outward at an increasing rate, driven by something we cannot identify, headed eventually toward a cold, dark, isolated future where even the cosmological background radiation will have redshifted beyond any detection. And somehow, in the middle of all of that, you are here, thinking about it. That is either the most improbable thing in the history of matter, or it is the most inevitable, depending on how you look at it. Either way, it is worth the sitting with. The universe does not want you to see most of it. It has hidden its majority behind walls of electromagnetic silence and quantum opacity and geometric separation and the cold arithmetic of cosmic expansion. But it left this small, bright, structured minority where you could find it and ask questions about the rest. And it made the rest leave fingerprints. Enough fingerprints that the questions are answerable, at least in part. Enough fingerprints that the work continues. Enough fingerprints that every decade reveals something the previous one could not have guessed. That is the kind of universe worth spending a lifetime in. And this is the kind of question worth spending a video on.